Hello, everyone. It is Wednesday, the 29th of October, 2025, and there are possibly monopoles that are being termed quasi-particles regarding magnetism in the absence of electrons that really put together a lot of the data I've been collecting and the research I've been doing regarding electricity and magnetism, this being a magnetoelectric cosmos or universe, light and sound expressed through or via or with electricity and magnetism at various strengths or in harmony when they're in balance. And so I'm going to be sharing a lot of videos on quasi-particles today from different professors just to see what their explanations are and see if this lines up to things that I have been trying to express or explain without a huge frame of reference. And but anyways, enjoy. This is Professor Claudio Castelnovo, a brief introduction to quasi-particles in frustrated magnets. And so here we go.
Conventional magnets, which make up for most of magnetic materials out there. But interestingly for us,
starting ahead because he hasn't really got into any outline or anything yet. And so it was over 6 minutes in. There was a brief intro. But anyway, this is going to start, I hope.
Not all. Some of them are frustrated and will come to understand what this means and give rise to a behavior that is very different, that goes under the name of spin liquid, generally speaking. And we will come to understand why the reference to a liquid in this case. And we will go through a little bit of modeling in terms of a general overview about these spin liquid systems. There are several interesting properties that would fill more than one talk and probably would make for a nice series of lectures. And I will not be able to cover them. In particular, degeneracy, topological properties, emergent symmetries. These are all interesting things that will be only hinted at in this talk. That is the reason. The reason for that is that I would like to focus instead on what are known as their quasi-particle excitations.
Before I get into the quasi-particle explanations that he's going to give, I haven't seen this video yet. I'm going to watch it with you. I did watch this Instagram clip on quasi-particles.
Particle, when it's a quasi-particle, of course. But to understand what that means, you have to understand that particles themselves are really just energetic excitation in the underlying fields that pervade the entire universe. Quasi-particles emerge from the complex interactions of those fundamental particles, but they only emerge in solids, liquids, and plasmas. Using quasi-particles promises to provide us with new materials, new technologies, things with really exotic properties. But it also makes us question whether fundamental particles really are so fundamental after all. To make a quasi-particle, you just take a material, often a metal, and put it under really, really high temperature or pressure or really powerful magnetic fields. And then you observe the collective behavior of the particles inside that material. Holes were one of the first quasi-particles to be discovered in the 1940s. It's sort of like the opposite of an electron, or the absence of an electron where one should.
Exactly, like I've said before too, when I've showed different experiments, just because you don't see electrons or like within like an area where there's force being applied on it, does not mean that it is empty space. It's not empty space.
B. And treating it as a particle has provided really huge leaps in technology. That's how we made the semiconductors that power pretty much all of our complicated electronics now. Even big companies like Microsoft are investing pretty heavily in quasi-particle research because of their promise to provide new materials. The very existence of quasi-particles and the fact that they're not particles makes you question, are the other particles really particles? Do particles come from the behavior of something else? We really don't know, but thinking about quasi-particles may lead us to a major rethink of how we think about everything.
Absolutely.
When is a part
photons, phonons, sound, light, all of that stuff that I've talked about, this absolutely has to do with this magnetic electric reality that is contained. And so I would be interested to see what Ken Wheeler and Austin Whitsitt, if they're going to look into this. If they do, I would love to get their feedback or their assessment on it, because they are very smart, and see what their thoughts are on it. because it goes against the this being like a strictly electric reality. Anyway.
And again, here I will go back to stressing the contrast with conventional magnetism and the type of excitations that you have there. In order to do that, I will pick one case in point, which goes under the name of the 8-vertex model, simply because it's easier to talk about a specific system than concepts in general. But then whatever we will discuss about this system is actually carries on to very easily to the broader class of spin liquid systems, frustrated magnets. And we will see that its classical behavior, meaning understood as a stochastic classical mechanical system, is already very interesting. The quasi-particle excitations are deconfined, they fractionalize, and we will understand the meaning of these terms throughout the talk. And they have very interesting topological properties, which, however, we will not be able to go into in any significant level of detail. Towards the end of the talk, I will try to deliver this first part of the talk in a progressive manner, making sure that I can bring along as many of you as possible to at least understand the fundamental principles that appear in the physics of frustrated magnets and spin liquids. In the classical sense, it's of course easier, and I would like to then stray into the quantum regime and see what happens when you introduce quantum fluctuations, because it's a very interesting change in the system, these systems, and also a very active and modern topic of research. However, the language here will become substantially more difficult, and I expect in these slides that I will actually be skimming through rather quickly, giving the fundamental concepts and probably not being able to cover anything in depth because it's far beyond the level that would be adequate for this presentation. But I would like to glimpse it anyway, if only for advertising, but also to give you a hint about what modern research in this area is about. And in particular, I will point at a very interesting regime that happens at finite temperature in quantum spin liquids. And that was actually something that I mostly credit my graduate student Olli Hart for, who has done a beautiful amount of work for his PhD in that area. And I list here 4 archive papers. Many of them have been published, but the archive references are easier, and I will give them again throughout the presentation. After the final rush through these very high level and slightly hard slides, I will come back to draw the point of this presentation in the conclusions and bring back down the understanding that we've developed through this chat for after about an hour. Okay, as I said earlier, I stress again, if I'm going too fast, too slow, or any feedback you want to give me, I can't hear anything at all. I can't see anything at all. So please type it in the chat and don't be afraid about it. No question is ill-posed or inappropriate. Just ask. And worst case scenario, I can defer the question to the end of the talk. And if not, I will use it and address it throughout to tune my presentation and make it as useful as I can for you, despite the double blind. So in order to introduce frustrated magnetism, let me take a step back and revise with you what conventional magnetism is, how we have come to understand it. And in order to do that, I want to do it in one of the simplest possible models for a magnet. Typical magnetic materials are crystals or lattice structures. So I will take a square lattice for simplicity, drawn here. In general, magnetic systems have atoms that have a magnetic moment, and the simplest approximation we can do is that this magnetic moment points in either along one direction, either up or down. So it takes 2 values essentially, and these are the arrows that I have sketched on this square lattice. Incidentally, this is also the first talk where I interfaced a little bit typeset slides with handwritten from a pad. My handwriting is horrible. And as you can all see, I will explain carefully through what I've written, so you won't miss anything because of that. And also rest assured that most of the slides are still typeset. So it's only a few of them that I decided to try and write out and see how they work. So with this model in mind, I will add one ingredient, which is an interaction energy, E. And again, in the spirit of keeping the model as simple as possible, this interaction has an energy strength, J. I hope you can see my mouse moving on the screen. If not, I'm still telling everything that I want to say, so it's not going to make a difference. Times the sum over the product of these spins. I will represent these spins mathematically as just numbers plus or minus 1. After all, they take only 2 values, so a down arrow is -1, an up arrow is +1. And we sum over nearest neighbor, that's the representation with the angular brackets here, of sigma I times sigma j. I take the constant j, which measures the strength of the interaction to be positive. And then you can see that this energy has essentially, for every bond, 2 possible values. If the 2 spins point in the same direction, as is illustrated here, the energy is minus j. If they point in opposite direction, the energy is plus j. So this energy term tries to favor the spins to point in the same direction. If they point in opposite direction, it costs energy. So, as we may be accustomed to, or as if you have heard, if you go take a system and you lower the temperature in thermodynamic equilibrium, the system will approach more and more closely the state that minimizes its energy. And so the low energy correlations in the system are the ones that are favored at low temperatures, are the ones that see the spins pointing in the same direction. Whereas at high temperature much larger than the energy scale J, the energy doesn't do much, and the spins are somewhat free to point up or down. What then happens in these systems, if you are tuning temperature, I've shown here as an axis temperature divided by J, just to set the units, you transition from this disordered state at high temperature where the spins point up or down to an ordered state at low temperature. At high temperature, clearly you have many different configurations that are equally good because every spin is more or less free to point up or down. At low temperatures instead, the spins tend to behave in the same way. They develop these ferromagnetic correlations, and so they are mostly up or mostly down. And in the limiting case where they're all up or all down, you only have really 2 configurations that are consistent with ferromagnetic order. And in this picture, typically, what you expect is that the transition of the system from the disordered to the ordered phase happens abruptly, happens at what's known as a critical point, where somewhat suddenly the system develops this order, ferromagnetic order, as you lower the temperature across it. The scale at which this transition happens, as indicated in the figure, is one such that the temperature is of the order of the coupling constant J in your system. Above this transition, the system is disordered, below is ordered, but the disorder above I quote here as trivial. Trivial in the following sense: if those of you are familiar with the concept of high temperature expansion, there is a way to compute spin correlations, and a trivial disorder, I would say, is the one that is continuously connected and largely represented by the leading order terms in high temperature expansion. For those of you to whom these terms don't make much sense, I just want to say the spin correlations that are represented here by the angular bracket of SISJ is just a measure of the probability of the spin at site J being up if the spin at site I is up. So you can see it's a measure of correlations. And the trivial aspect, the high temperature expansion, simply tells you that the leading order in the high temperature expansion simply tells you that this quantity is given by the energy term EIJ divided by temperature with a minus sign in front. What's the energy term? Well, the energy term is literally the IJ term in the energy, the coupling constant of that. So in the form of the energy that we had before, that constant is minus J if I and J are nearest neighbor, and it's 0 otherwise. And so if you put a minus in front of it, this trivial disorder tells you that essentially the probability of a spin being up, given that another one is up, is controlled or in magnitude by the ratio of J over T, and it's 0 if I and J are larger than nearest neighbors. It's trivial because the amount of correlations that you have in your system are essentially dictated by what you put in as an initial information or ingredient, which is the Hamiltonian or the energy itself. The situation changes dramatically if you go in the ordered phase, when knowing one spin being up tells you that with a good probability all the others are up, no matter how far they are. And clearly, this idea that the correlation is just minus Eij divided by T breaks down as you approach the critical point. But in a conventional magnet, it's only approaching the critical point and relatively close to it that makes this picture break down. And otherwise, at higher temperatures, this is fairly respected or obeyed, and the disorder is what I call trivial. This is, however, not the end of the story of magnetism. Otherwise, we wouldn't have been having this talk at all, actually. There are systems where this picture is prevented to occur by the fact that the system is unable to minimize all terms in the energy.
I'm going to start with another video because, again, there's not a lot out there. I did watch this yesterday, and it was sort of interesting from 2 years ago. How are quasi-particles different from particles? Maybe this is a better start state because this is possibly an introduction to people to what I believe to be monopoles, or what they're calling quasi-particles actually is, which is revolutionary for how we define the laws of physics.
TV for supporting PBS. The device you're watching this video on is best understood by thinking about positive and negative charges moving around a circuit of diodes and transistors. But the only elementary particle actually flowing in that circuit are the negatively charged electrons. And yet those flowing positive charges are there, in the form of a particle you may have never heard of. Your device works because of quasiparticles, a class of strange emergent behaviors of nature that enable
our device, that he said device works because of quasiparticles, just like this cosmos.
Our most important technologies and are behind some of the weirdest phenomena that we have ever encountered. Let's begin our discussion of quasiparticles by talking about the particular quasiparticle that lets me talk to you about quasiparticles right now. Now, electrons, which are regular particles, are pushed around inside electrical circuits, but that's only half the story. In the semiconductors that make up transistors, diodes, and solar cells, the pushing around of a quasiparticle is equally important. Let's look at the material that is central to all modern electronics, silicon. The silicon atom has 4 electrons in the outer or valence shell. Atoms are most stable with full valence shells, which means 8 electrons. That's why silicon likes to form covalent bonds with 4 other silicons, and each of those with another 4, forming this tetrahedral crystal lattice. We're going to depict this as a square.
Tetrahedral crystal lattice. I have a tetrahedron. I have 2 glass-shaped ones that I have as ornaments that I bought like 4 or 5 years ago. This is literally confirming like a theory.
A grid in 2D to save on animation costs. The valence electrons are now locked in place by the now full valence energy level, but they can still get bumped up to higher energy states, say by thermal vibrations, or in the case of solar cells, by a photon, at which point the electron is free to move from atom to atom, for example, if pulled by a voltage applied across the silicon. Meanwhile, the gap left by this electron allows some movement in the valence shell. A neighboring electron can move there, and its neighbor can fill the new gap, etc. It looks like the hole moves around, and under a voltage, the hole moves in the opposite direction to the flow of electrons. This is our first quasiparticle. It's an electron hole. It has an effective positive.
Not an electron hole. It's void of electrons, but not of protons or photons or phonons, whatever you want to call them. Magnetic particles, whether it be like a pushing or a pulling, attraction or repulsion.
Positive charge due to the charge of the nucleus not being properly cancelled by electrons in that location. It even has an effective positive mass. We can model it as though it's a real particle. To see how this quasiparticle is more than just a way of looking at things, consider perhaps the simplest semiconductor device, the diode. Diodes allow current to travel in one direction but not the other. They consist of two layers of silicon. On one side, there's an excess of valence electrons, and on the other, a deficit. This is achieved by doping, contaminating each layer by a different element. On one side, we sprinkle the silicon lattice with a tiny number of atoms that have 5 rather than 4 valence electrons. Phosphorus is a popular choice. Those extra electrons are more free to move around because they aren't part of the crystal bonds. This is an N-type semiconductor. N because the flowing charge is negative. The other side is doped with atoms that have 3 valence electrons, frequently boron. Now electrons on that side can move a little bit. They can shuffle to fill the gaps in the underfilled valence shells. So we have flowing positively charged electron holes and a P-type semiconductor.
Just say
in a
charged holes.
diode, N and P types are fused together. At the P-N junction, extra electrons in the N-type diffuse into the gaps in the P-type, so we end up with a region where all valence shells are filled, so charge can't flow. Apply a voltage in one direction, and the holes and the electrons flow away from this junction, expanding the non-conductive region and shutting down the current. But apply a voltage the other way, and the electrons and the holes are driven towards the junction, causing it to narrow and the electrons to hop across, enabling the flow of electricity. That's the diode, a valve for electricity, and these P-N junctions also drive solar cells, LEDs, and transistors, and they all depend on the behavior of these quasiparticles, these holes. Now, you might argue that electron holes are just a convenient way of looking at things, but that they aren't real like electrons are. After all, if you melt the silicon, the electrons still exist, but the holes don't. In a sense, that's right. Quasiparticles are emergent from the behavior of a particular configuration of matter, just like states of matter, which we talked about previously. But at the very least, quasiparticles make it much easier to model certain physical processes like semiconductor junctions, and in other cases, they are indispensable. Let's explore one of those cases. We'll stick with our silicon crystal. We have one quasiparticle from making a gap in one spot in the electron energy level, but we can make another one by making a very different tweak to the local energy in the crystal. Another way energy can be stored in the lattice is in the vibrational modes of the atoms. Think of the covalent bonds as springs. So when an atom receives pressure, it will move, pressing on the springs and causing other nearby atoms to move as well. In this way, vibrational energy can move around the lattice. But this seems a bit more like a sound wave than a particle. In fact, sound waves in solids do propagate exactly like this. But remember that we're dealing at the quantum scale here. Those vibrational modes in the crystal are quantized, similar to electron energy levels. In this case, the crystal lattice can vibrate at any frequency, but the amount of energy in each vibrational mode can only go up in discrete chunks. That means vibrational energy also gets transferred in discrete packets. So now we have something like a particle, a quantum of vibrational energy moving around the lattice. This new quasiparticle is called the phonon. I said that sound is transmitted through solids via these vibrations, so this makes the phonon a quantum of a sound wave, similar to how a photon is a quantum of light, of an electromagnetic wave. The analogy is not a shallow one. Phonons behave in many ways like light. They travel at the speed of their wave type, sound in this case. They have energies equal to the Planck constant times their frequency. They are boson-like in that you can stack multiple phonons on top of each other in a single vibration. Compare that to electron holes, which are fermion-like in that you can only have one at a given spot at one time. As well as being a quantum of sound in solids, they are also the quantum of heat. After all, heat in solids comes from the vibrational motion of its atoms, and that vibration is transferred around by phonons. You can think of sound as being like a coherent beam of phonons, like a laser, while heat is a random buzz of phonons. Understanding the behavior of phonons is critical for understanding the behavior of both sound and heat in solids at the quantum scale. And phonons are also really important for your computer, which, as you know, can get hot. Energy is often transferred between phonons and other particles, quasi and real, and modelling this is needed for modelling the behaviour of heat on the quantum scale. For example, electrons travelling through a circuit encounter resistance. Basically, they have collisions, which can be electromagnetic interactions with other electrons or falling into a hole, etc. In doing so, they can dump their energy into a vibrational mode and create a phonon. This manifests as heat. The heat due to electrical resistance is one of the main limitations on running your computer as fast as you might like to. But quasiparticles can help there too. But before we get to that, a quick recap. We now have two types of quasiparticle. Holes, which are like quasi-electrons, or perhaps quasi-positrons, and we have phonons, which are analogous to photons. Now, elementary particles can be combined into composite particles. For example, an atom is composed of quarks forming the nucleus, and electrons bound to that nucleus by the exchange of virtual photons. Believe it or not, we can create composite quasiparticles in a similar way. And, as it happens, the new quasiparticle that we're going to create can help us with this electrical resistance problem. You may have heard of a little something known as superconductivity. When you cool a metal to near absolute zero...
Like, is it electric resistance or like magnetic influx or another term? I don't know.
The electrical resistance also becomes zero, which in turn creates many cool interactions with electromagnetic fields like levitating magnets, which you can then use to make superfast trains.
The stronger force.
We'll do a deeper dive into superconductivity another time. Today, I just want to show you how this phenomenon is enabled by quasiparticles. Metals form from crystal lattices similar to silicon, but they are much better conductors because they don't use up all of their valence electrons in the bonds of the lattice. At a voltage, and those electrons are free to travel through the structure as electrical current. But of course, we have them pesky phonons, which at any significant temperature just add up to a lot of random jiggling of atoms, aka heat. That motion, as we know, causes resistance. Electrons are jostled, exchanging phonons in both directions with the atoms, which prevents a smooth, streamlined flow. You might think that cooling down the metal alone would be enough to enable higher conductivity, but it's not the relative stillness of the atoms that does this directly, it's something much more interesting. Very low temperature means few random noisy phonons, which in turn means that coherent structures of phonons become possible.
Bingo.
In fact, it becomes possible for the phonons to take on another property analogous to the photon. They become the carrier of a force. In this case, a quasi-force that can actually bind electrons together. Normally, we think of electrons as repelling each other via the electromagnetic force mediated by photons. At the same time, the negatively charged electrons in a metal lattice attract the positive nuclei. The nuclei get tugged a tiny bit in the direction of a free-moving electron, and that tiny increase in positive charge can in turn attract more electrons to that location. Ideally, that first electron is part of an electric current, so it just moves along. The nuclei spring back again and actually oscillate. They take a little bit of the original electron's energy in a vibration that's part of a phonon, mixed up and indistinguishable from all the other crazy oscillations across the lattice. Any electrons that were attracted by this momentary convergence of positive charge are jostled so much that this effect is tiny. But if the metal is really cold, like near absolute zero, then the phonons induced by this attraction of nuclei to a passing electron can be a dominant vibrational mode of the lattice. A stream of electrons in one direction sets up a sort of resonance in the vibrational modes of the lattice, effectively binding pairs of electrons together. In a very real way, these electrons are bound together by the exchange of phonons, similar to how electrons and nuclei are bound together by the exchange of photons. And this pair of electrons is our next quasiparticle. It's the Cooper pair. Now, it's really a fair bit more complex than this. The pairs of electrons are bound over large distances, not separated by single atoms. And it's not simple to say which electron is bound to which other. In fact, a network of Cooper pairs move together in the mutually induced resonant oscillation of the metal lattice. An amazing thing about Cooper pairs is that they behave like bosons. Each electron is spin half, making them fermions, but two electrons together have spin 1, like a photon,
Like a photon.
and that's for reasons that we can't get into.
Like a
But
photon.
this means that they act like photons in that many Cooper pairs can occupy the same quantum state. In fact, at very low temperatures, all of the pairs in an enormous network of flowing electrons can all occupy the lowest energy state. They don't have the energy to excite new phonons, and so they don't. This means they stream through the lattice with zero resistance. As I mentioned, there is a lot more to the story of superconductivity, and we will come back to it. And these Cooper pairs are also responsible for superfluidity. They are in general pretty super as far as quasiparticles go. There are many quasiparticles beyond the few that I had time for today. For example, quasiparticles appear in the lattices of quantum spin, like magnons, quanta of waves in that lattice, or skyrmions, which are localized stable topological field configurations, sort of like knots, all very important for the emerging field of spintronics. In superfluids, we have rotons, a quantum of the vortex in the fluid. The roton is a quasiparticle enabled by another quasiparticle, Cooper pairs, which in turn are enabled by yet another quasiparticle.
And this is possibly what the sun creates above us, this like spiral or funnel as it goes higher and lower within this contained environment, which also assists with this energy flow.
Phonon. It seems that quasiparticles can build into complex hierarchies just like regular particles. Which shouldn't be so surprising because quasiparticles are like regular particles in so many ways. After all, the elementary particles like electrons, photons, and quarks are just excitations in the elementary quantum fields. But a field is just some property that can vary over space. Another field could be, say, the number of electrons in the valence shell of a block of silicon. And it turns out that any field, elementary or not, will give rise to particles as long as that field has quantized energy states. A crystal lattice supports many fields. The quantized number of valence electrons, or the many quantized vibrational modes in its bonds. We now know of dozens of quasiparticles, but there are no doubt many more waiting to be discovered, and some may enable new technologies just as cool as the superconductor or as world-changing as the transistor, all part of the magnificent complexity emergent from simple fields spanning space-time. Thank you to Magellan TV for supporting.
Very interesting. Very interesting. Okay, so I'm back on to Professor Claudio, because again, this might be a long video. This is all about redefining what magnetism is.
Let me go back to the toy model we had before. This interaction
magnetism.
nearest neighbor, sigma I, sigma j, times minus j, constant. When we looked for the lowest energy correlation, we've seen that for two spins, you just put them both up. But in fact, you can do that systematically across the system, and you can make every term, additive term in the Hamiltonian, minimum at the same time. And that's done here. If all the spins are up, every single bond is happy, meaning it's in its lowest energy state. This is, however, not always the case. And the typical example that gets quoted in most textbooks and talks is if you have three spins around a triangle. Let's take the same interaction, but in this case, antiferromagnetic. So I put the sign in front of J to be +1. Now the spins want to be up, down, next to one another. So if we start with a spin up, the next one is down, and then we have a conundrum for the third one. If it's up, this bond will be ferromagnetic, therefore costs energy. If it's down, this bond is ferromagnetic and therefore costs energy. And we cannot avoid that conundrum, so the third spin can be either up or down. It doesn't matter. You cannot minimize all terms in the Hamiltonian or energy. You are necessarily forcing one of the bonds to be a high energy one. What happens in this case, very typically, is that the transition temperature is suppressed. If you remember, if we go back to the model here, the ordering that we saw at low temperature was favored by the ability to minimize the energy by putting all the spins in the same direction. Now, if we're making this task impossible, it's conceptually intuitive that we are going to make it harder for the system to develop this ordered state. And therefore, if it happens at all, it would happen at lower and lower temperatures. And intuitively, that's all I'm going to convey. I'm not going to give you an explicit example at this point. But what happens is that TC gets suppressed to a value much larger than J, and the phase diagram that we are accustomed to in conventional magnetism gets replaced by this temperature arrow, where there is a disordered phase. You cross the point where the temperature is of order J, but the system doesn't order until a much lower value of TC over J that's much less than 1. And then the question is, what happens in this intermediate regime that we have now access to because of frustration? And what we learn quite generally here is that the trivially disordered phase that happens at high temperature smoothly crosses over into this question mark region before a proper phase transition happens to the ordered phase. This question mark region now has a very peculiar nature because it has no long range order. There hasn't been any phase transition happening yet. There's no symmetry breaking. Order hasn't developed. On the other hand, now temperature is smaller than J, and the high temperature expansion that was helping us understand what type of correlation we had before in the system goes out of the window. The correlations can become very important and much more elaborate. Yet the system remains disordered, but in a correlated sense. And it's this notion of correlations coexisting with strong correlations coexisting with disorder that has been the appealing and characteristic features of frustrated magnet and has been broadly dubbed spin liquid behavior.
Spin liquid behavior.
In understanding this behavior, people have been studying systems, toy models, and realistic Hamiltonians, and so on, and even experimentally several materials are known where different properties have been uncovered, and it has proven to be quite an unconventional phase of matter. It has an extensive degeneracy. When you try to minimize the total energy, because you cannot do it term by term, you end up with a lot of redundancy because, as in the case of a single triangle, we had the third spin that we could put up or down equally, and everything is fine. When you do it for an extended lattice, you realize that you have a lot of freedom in changing the system while maintaining the same total minimal energy. This extensive degeneracy at the quantum level evolves into what are known as quantum highly entangled quantum states. The symmetries of this system become very peculiar. There is an emergent and typically gauge type of symmetry that appears in this system. And this is quite striking because from high energy perspective and standard model, our understanding of the universe, we always expect that as we go from high temperature to low temperatures, the symmetries are broken, and the system, as the system becomes always less and less symmetric. The highest version of the symmetry is the universe. The highest symmetric version of the universe will be the hottest, closest to the Big Bang formulation, grand unified theory, and so on. It's only through cooling down that spontaneous symmetry breaking occurs, and different type of electromagnetic field or other gauge fields and particles appear because of this breaking of the symmetries, Higgs mechanism, and so on. These systems are very peculiar in that respect because you reach a low temperature state where the system exhibits more symmetries than the disordered phase at higher temperature. And this took a while to fully understand and grasp from a theoretical point of view. Together with these emergent symmetries, you end up with topological properties that are quite unusual and have been the focus of attention over the past 20 to 40 years. for a lot of interest in storing information in a robust way, etc. And a dual side to these are the nature of the excitations in this system that are very exotic and again, once again, very different from conventional magnetism. Now, in these slides, I throw around a lot of buzzwords that I am not explaining in detail. As I said, it would be the subject of several lectures if we really wanted to go together through all these topics and make sure that everyone understands them. At this point in time, I will leave most of these as buzzwords for you to be curious about if you want to learn more, or keep them in mind when you'll encounter them perhaps during the course of your studies. The one aspect, however, that I want to focus on and that I will hopefully be able to clarify further and come to a common understanding thereof are precisely these exotic excitations. And as I have done in regards to introducing frustrated magnetism versus conventional one, I want to once again take a step back and look at the type of excitations that we expect in a conventional magnet to be able to then contrast them to what we see in a frustrated or magnet or spin liquid. Okay, let me just take one moment of break to allow people to process for a second. And if you have questions, please do. I do not see any on the chat, but
green is the middle point for the colors of the rainbow, for the chakra systems, all that stuff. And we see more shades of green than any other color. Fun fact.
Pop them in at any time. Okay, so step back. Excitations in conventional magnets. How do we think about them? Well, we have a disordered phase where the spins point whichever direction. In that set phase, there isn't really a well-defined excitation to speak of that is particularly useful to formulate. What we want to look at is the low temperature regime where the system orders. And now, if you do that in a perfect manner, ideal ground state, zero temperature, all the spins are aligned. You want to maximize the ferromagnetic interactions or minimize the energy, and therefore put all the spins pointing in the same direction. What kind of excitation can you expect then? In a toy model that we discussed earlier, we would just take one spin and reverse its direction. And that's what I've done in the middle drawing here. One spin points down. And if we do that, we clearly see that it's no longer a minimum energy condition because it's pointing against the direction of its neighbors, and therefore it costs energy. As a matter of fact, we can draw a green line around it as shown, and across this line, the interaction is broken. It costs energy rather than being in the minimal energy state. If we want to progress from there, we can flip more spins. And what happens is that either you create other islands, or you can enlarge this island, as I've done here in the drawing. And the property that you will see is, again, that you're going to have a patch of downspins in a background of upspins, however you want to look at it. And the boundary between them, shown here by a green line, is a costly boundary through which every bond costs energy because it's in the unfavored state. These up and down patches are called domains, and the excitation, meaning where the system pays energy in order to allow for different patches to coexist, are lines around these domains. These are the green lines. These green lines are either closed or they terminate at the edge if you have an edge of the sample, but they cannot just stop in the middle. The excitations are domain walls between different domains. Let's now think about what happens in a frustrated magnet, and in order to do that, we need to discuss a case in point. We need to actually go and look at a specific system so that we can understand better what these unconventional excitations are and how unconventional they are compared to the scenario that I just described a moment ago. The model I chose to discuss today goes under several names. One of the perhaps most famous one is the 8-vertex model. And you will have to bear with me as I introduce it. As you can imagine, frustrated magnetism is very interesting, but it was discovered very recently. And one of the reasons is because most magnets are, in fact, not frustrated. And so you can imagine correspondingly that if you want to devise toy models that describe frustrated magnetism, you'll need to do something different with respect to the typical toy models that have been encountered so far. So the first difference is that I'm going to put the spins, these objects that point up or down, or in this figure I will call just plus and minus 1. I will put them on the bonds rather than on the sides. So there are these black dots, again on a square lattice. And then I will put an energy. This is a toy model. It's particularly simple for us, but slightly unphysical. So I'm not selling it as a good, faithful representation of any magnets in nature, but it's good for our understanding. And so I endow it with an energy, which is again minus J, sum over all the sides S. S is going to be the label of all the sides of the square lattice. I will use I and J for the spins, and later I will use P for the plaquettes. This energy is again minus J sum over all sides, but instead of having 2 spin interactions, which is what we had in the model I introduced earlier, we are going to take the product of 4 spins. The 4 spins that are surrounding a site S. So I belonging to S is these 1, 2, 3, 4 spins connected by the dashed green lines here. For J positive, you can easily see that this interaction wants to have this product to be plus 1. You're taking the product of numbers that are plus or minus 1, so the only outcomes that you can have are plus or minus 1, and with J positive and a minus J in the energy, what you want to end up with is the product equal 1 in the lowest energy state. Now, if you're taking 4 numbers that are values plus or minus 1, and you want their product to be plus 1, you can immediately realize that either the 2 are plus and 2 are minus, or 4 are plus, 4 are minus. I've drawn a few configurations here, and it probably shouldn't take you too much by trial and error to think of how many configurations you can have that are distinct, and you realize there are only 8 of them. And that's the name 8-vertex model. These are not all the configurations. Well, clearly, if you have 3 plus 1 minus, that's not a minimal energy state. For example, this vertex here is not in the minimal energy state. How many states do you have in total? Well, you have 4 objects that can take 2 value only, so it's 2 to the power 4, 16. So the 8-vertex model, for every vertex, only 8 are minimal energy, the other 8 cost energy. There are the usual characteristic properties if we ventured into it. I said I wouldn't discuss this much, but I thought I'd mention them very briefly, and if people have questions, I can elaborate more at the end of the talk, but this model is extensively degenerate. If you look at how many configurations minimize the total energy of the system, there are actually exponentially many in the volume, and there are nice estimates of this, but also exact calculations. In this case, the model is very simple. There are also unusual correlations. Unusual because you can actually demonstrate that the correlation between 2 spins is 0, meaning that the probability of a spin being up, given that another one is up, is exactly a half. There is no information whatsoever shared between the 2 spins, unless you're talking about the same spin, obviously. However, there are topological properties that are very interesting. They are non-local, so you can encode non-local information in the states of this system that is protected with respect to small deformations. Nonetheless, these again, I'm going to leave as buzzwords to stimulate your interest and curiosity should you want to look into any further. The focus of this talk is the excitations. Once again, we have a system that is made of objects that can point up or down, plus or minus. And the first place we want to look at, if we're looking for excitations, if we want to look at violations of the minimal energy condition, is to flip one of the spins, change a plus to a minus or a minus to a plus, and see how we can understand that. So I've drawn here a configuration where I no longer use the black dots for the spins. So the spins are just plus minus on the bonds. And if I haven't made any mistakes, you will see that every vertex has either 2 pluses and 2 minuses, or 4 pluses or 4 minuses. So every vertex is now happy in the minimal energy state for the Hamiltonian, or the energy that I gave earlier. Now I'm going to take the spin circled in yellow here and flip it in the same way that I did with the intermediate configuration in the conventional magnet earlier. So I picked that one and then flipped it. I'm going to do the same now here and flip this one. The moment I do that, you see that the two vertices next to it now cost energy. This one is 3 plus 1 minus. This is 3 minus 1 plus. The product of the spins is -1, and that's an excited state. That's an energy cost in the energy we had before. In general, thinking about what we know for conventional magnets, so far there's nothing surprising. We would expect that if we now go and flip spins next to this, we would build a patch of flipped spins that costs energy all around it. The idea of a domain with a domain wall surrounding it. However, if we try to do this, say, by taking this minus spin here and circled in yellow, and we flip it, something very special happens. Now, this new vertex here has 3 plus 1 minus costs energy, but the one in between is 2 plus 2 minus has gone back into its minimal energy condition. This could be a fluke of actually being flipping just spins next to one another. Okay, we can keep going. If we flip this one circle now, and then maybe the other two, this one and that one, we see that the process repeats. If you check carefully, the black dots highlight vertices that cost energy, but in between, all along where we flip spins, there's no trace, energetically speaking, of the fact that we have made a change to the system. All the vertices in between have gone back into their lowest energy state. This tells you that even though your initial excitation is a single spin flip, that's the simplest move you can do in the system, actually, this breaks down or fractionalizes into two entities that have a life of their own, as defined by the fact that you can take them apart, these entities defined by the product of the sigma I around the vertex to be -1, they can be separated at will. As a matter of fact, there is no energy cost to separating them, which means that they are trivially deconfined. Deconfined particles are particles where the energy cost to take them from nearest neighbor to infinite distance is finite, and therefore any thermal equilibrium will see them separated with a certain finite probability. The typical counterexample is the two endpoints of a spring. Yes, you can pull them apart, but their energy grows linearly, Hooke's law, so long as the spring doesn't break. That means that, yes, you have two endpoints of a spring, but on the other hand, they should really be considered as a single object, the spring, because they are bound together, they are confined to one another. In this case, the spring is infinitely flexible, you don't even know it's there, and therefore each endpoint is a particle of its own. And the single defective sites are essentially these elementary excitations that are half a spin flip. And the excitations you have in the system is a lattice gas of these black dots, of these defective sites that can hop around the system, they can random walk, and they can occasionally be created in pairs, or they can annihilate in pairs, but they cannot just evaporate or disappear on their own. So that's the contrast between conventional magnets and spin liquids. In one case, we have this understood scenario where we have domains of upspins and domain of downspins separated by continuous, typically closed lines, unless they end at the boundary, which are the domain walls. And the domain walls can be deformed, they can move, but they are strings embedded in 2D for two-dimensional systems. For frustrated magnets, for this spin liquid that I've been discussing, the excitations are instead point-like objects. They can only be created in pairs or annihilated in pairs, much like electrons and positrons if you want, but they're otherwise free to move around the lattice as particles, random walking across, and defining, if you want, what go under the name of reaction diffusion processes, if you're familiar with the terminology. This is starting to give us a picture of how exotic the excitations in these systems are, and why they attracted so much attention. A lot of the attention came, of course, from the topics that I did not cover in this presentation, including emergent symmetries and topological properties, degeneracy and entanglement. But these quasiparticles already give you a flavor of the type of interest that these will generate, and the fact that their response to a magnetic field, for example, or their properties in general, will be very different. If you think about the heat capacity or the susceptibility of a material, they are related to their energy fluctuations or their ability to respond to an applied magnetic field. And you can intuitively see how this will be very different if your excitations, your energy excitations, are necessarily continuous strings, or they are point particles that can percolate and annihilate. Vice versa, if you think of applying a magnetic field which will favor spins up versus spin down, in one case, you will be stretching domain walls until they become infinitely large and one domain takes over. In the other case, you will be moving around point particles across the system, leading to a very different type of response. I hope that with what we've covered so far, I managed to convey a bit of a basic understanding of frustrated magnetism, contrasting it with conventional behavior, and also a flavor about this fractionalization and deconfinement of its excitations that make it so different from conventional magnets, and that illustrates why this spin-liquid regime attracted so much attention and was so interesting and surprising as it got studied over the past about 50, 70 years. However, this whole phenomenology acquires yet a new level of complexity and interest the moment we bring in quantum fluctuations. And at this point in time, it's where I will progressively switch the pace and the language of the talk. I will try to maintain some level of accessibility, but in order to be able to touch upon these quantum mechanical properties, which I think are actually very fascinating and interesting, and it would be a pity to limit the discussion about spin liquids to the classical world. On the other hand, they will become substantially more challenging to follow. So I'll do my best. Once again, if you can, if you have access to the chat, let me know if you have questions, and I specify what I can. And at this point in time, I think taking home the high-level messages is more important than the fine details. The fine details would require a lot more technological, a lot deeper technological understanding of the math and physics underlying it. On the other hand, as I said, it would be a pity to stop here. So I would like to see what happens to this 8-vertex model the moment we introduce some quantum fluctuations. So that's what I'm going to do in the next few slides, and then I highlight why it's so exciting and interesting and why it's a currently active topic of research in some respects that I will illustrate before I bring this talk to a close. I am vaguely aiming to end around 7:20, 7:25, if I remember correctly, the start time. But if the organizer could put in the chat roughly when they would like me to end, I'll appreciate that, and I'll try to aim for that time, whatever it is that they're going to say. While I wait for that feedback, I'll continue, and we're going to start with our Hamiltonian, HJ here. Sorry, I used the letter E earlier. At this point, I will switch to H, which is a typical quantum mechanical formulation notation for a Hamiltonian. But this term is exactly the same that we're accustomed to, the sum over sides of the product of the sigma z of sigma spins around the star. And I will give it a component z because I want to introduce quantum mechanics, and I will do that by introducing non-commuting operators. For those of you who are familiar, this would be Pauli matrices. For those of you who are not familiar, I will be introducing the x component of the spin, which in quantum mechanics does not commute with the z component. And I will do that in a uniform manner, so just a uniform transverse field of strength T here, where the strength T is sufficiently smaller than J so that it's not going to spoil the physics we have been discussing, but it will add to it. And in this language, what happens is that the sigma x action, this transverse field term that I add, by not commuting with sigma ix, will cause spin flips. So it will do exactly what we have been doing by hand here. We see that we picked a spin and flipped it, and then picked another one and flipped it, picked another one and flipped it. And you could have thought about flipping that spin by hand, or being some kind of thermal fluctuation that causes it to change its state. And now, by going to the quantum world, we're actually adding a physical term in the Hamiltonian of the system that causes spins to flip. And the symbol T is the amplitude for these flips. So you can easily say or realize that in the context of what we just explained earlier, the ability to flip a spin, it means that we are giving dynamics to these quasi-particle excitations. So they are allowed to hop around, not just by hand flipping spins or by thermal fluctuations. There's now a quantum amplitude T for such an event that corresponds to a quasi-particle moving from one side to another. So the quasi-particles acquire what we would term a tight-binding Hamiltonian. This, if you have a quasi-particle to begin with, which is not a given, if you're at very low temperatures, quasi-particle are excitations that get suppressed. And so this term would not be able to act in the ground state of Hj, other than acting perturbatively. And if it acts perturbatively in ground state, you can see that if you flip 4 spins around the plaquette, say take these 4 spins here, because you're flipping 2 spins for every side, you maintain the minimal energy condition for every vertex according to Hj. And so that is able to act within the ground state without creating any excitations. And that adds a perturbative contribution to the Hamiltonian that we call Hj bar. It's important. And in a cute way, for this very simple model, it takes a form that is very similar to Hj itself, but it's now sum over plaquettes, the product of around the plaquette of the x component of the spin, where this perturbative coupling constant J bar can be computed, and it's of the order of T to the 4 over J cubed. It's not important how we arrive to this formula, but you can clearly see that if T is smaller than J, well, T over J cubed is a small number. And so we expect generically J bar to be much smaller than T, which is smaller than J. The beauty of having gone into this quantum world, and if you haven't understood or followed the details, don't worry, what I say next will hopefully bring you back into some effective understanding, even if the mathematical details are beyond your background at the moment. Well, the beauty of this is that if you now combine Hj and Hj bar, you build actually very famous model proposed by Kitaev in 1996, but then explained in a later paper in 2003 in a review, which goes under the name of toric code. Hj is the term we are accustomed to. It favors the product of the sigma z component of the spin around the star to be +1. That's what we have been discussing so far, and hopefully I did a sufficiently good job that by now this looks familiar. And then Hj bar, with its very similar form, favors the product of the sigma x component of the spins around the plaquette to be +1. The beauty of this very simple toy model is that these two conditions can be met simultaneously, even though sigma x and sigma z generically don't commute with one another. This is very unusual and very peculiar to this model, and that's what allows us to make a lot of progress in understanding its behavior, which is generally not affordable, and one of the reasons why I started with this model to begin with. And I would refer to further studies in order to see how this is done, but I want to give a flavor of the excitations, again, which are the topic of this presentation. And the elementary excitations take now 2 forms simultaneously. Well, there are 2 types, sorry, I should say, not take 2 forms. There are 2 types of excitations. The star defects are the ones that we've been discussing earlier. I will give them a name now just to distinguish them, and I'll call them spinons, but it's exactly the black dots that we were looking earlier moving around. The product of I belonging to S of sigma IZ is -1, and they have an energy cost which is controlled by the coupling constant J. Then there are simultaneous defects in the other term of the Hamiltonian. There are plaquette defects. They are called visons. And now they are product of the sigma I X component of the spin around the plaquette being -1, and they cost an energy controlled by J bar. What we have done by adding quantum mechanics is essentially we have doubled our excitations in the system. We now have spinons and visons. They talk to one another, but they essentially are excitations in two different components of the spins. So what's interesting? Well, it's interesting in the way they talk to one another. Because while single-handedly, spinons and visons are bosonic particles that are equivalent of quantum mechanical equivalent of particles, random walking particles that hop around, barring the ability to create and annihilate in pairs. That's a further complicated detail, but otherwise they are these random walking particles. Their mutual knowledge is actually very peculiar because it goes under the name of mutual semiotic statistics. If you have a spinon in your wave function and a vison at site S and plaquette P, if you take the spinon around the vison and bring it back to S, to its original location, the wave function picks up a minus sign. If you have fermions or bosons in your system, this is a fundamental identity physically, and that minus sign cannot be there. The difference between bosons and fermions is that a boson, you can exchange particles and they keep the same sign of the wave function. In the fermions, change sign, but then if you do a full swap, you go back to a positive sign. These ones are half fermions. You have to go around the particle twice to leave the wave function unchanged. And this clearly tells you that in your motion of the spinon, say a spinon here moving around and then getting to the second position here, the path will matter with respect to the background of vison. Say you have a vison at plaquette P, this yellow path here or this yellow path here will be different quantum mechanically precisely by this phase factor -1 that is attributed to going around the plaquette or not. This leads to an interesting interplay between these two that is purely due to this, what's referred to as anionic statistic, which is a key feature of this spin-liquid behavior. It's a close counterpart to their topological nature, as a matter of fact. Now, this is the physics of excitations. And if you really take the system to zero temperature, you see none of it because excitations cost energy and they would not be present. So we have to think about how to put them in. Of course, nothing stops us from looking at a state that is higher in the spectrum, an excited state of the system. But alternatively, we can think of raising temperature. The more temperature, thermal energy we put in a system, the more excited states you allow it to access, and therefore the more likely it is to exhibit some density of excitations. And that's the route that I would like to highlight here in bringing the talk to a close. And looking at these systems and these excitations, when we look at the temperature axis, and it's convenient to take this temperature axis and put all the energy scales that we have encountered so far on it. The largest one is J, the one that would like to not have spinons because spinons cost energy J. Then we have the smaller energy scale T, that was the one that was allowing the spinons to move around and hop. This generated dynamics for the spinons, but also generated this perturbative J bar term in the Hamiltonian, which is the third energy scale, and that lives much smaller on the temperature axis, much further down in the temperature axis because it's much smaller than the other two, being a perturbative process. And then I would bring your attention to this intermediate temperature region that is pretty broad between J bar and T. This is an interesting temperature region because it's the first temperature region where we start being able to encounter some quantum mechanical effects in this system. Ultimately, if temperature is large enough, everything is going to be washed out. And in this region, we expect the spin-ons to be few because temperature is substantially smaller than J. And temperature is smaller than T, so they're hopping around coherently. So they really behave like quantum mechanical quasiparticles. On the other hand, the visons are thermally populated, they're dense and incoherent because their temperature is larger than their energy scale. So they have a lot of them floating about. And this intermediate temperature regime is what we have been investigating together with my graduate student, Olli, who's done a fantastic job actually at obtaining some really impressive results. And also, it's actually, coincidentally, it's a subject of one of the Part 3 projects that I have offered this year, trying to investigate this regime. It's intermediate between classical and quantum behavior. You're mixing both ingredients. It's the highest temperature where you can expect some quantum spin liquid behavior to be observable. And in fact, by studying this regime, we realized that there is a lot of interesting features that were not necessarily expected to begin with, and a lot of interesting physics come into play. The fact that you have some classical behavior in the system produces some self-generated disorder in the spin-on motion that leads to localization, statistics-driven phase separation, scar effect, etc., which are part of the frontiers and very interesting directions of modern condensed matter physics. Generally, a framework of this regime is unfortunately still unavailable, but there are beginning to be quite a few interesting case studies out there. And there's a body of knowledge that's being developed into an interesting and beginning to be coherent picture of this regime that we look forward to investigate further. And now I won't have a chance to go through these, but I would like to flash a couple of slides as advertisement of Olli's work and the beauty and intricate questions and open issues that are still there in quantum spin liquids, in particular in this finite temperature regime. And then I will come back to bring the talk to a close. One of the interesting things is that as the spin-ons hop around and there are visons in the background, this property that when you wrap the spin-on around the vison, you pick up a minus sign in the phase function, minus sign in the wave function, is equivalent to moving an electron on a square lattice where plaquettes where you have visons are threaded by a pi flux, a magnetic flux. And this is a problem that has been studied earlier. And so you can use part of that language to try and understand the behavior of these systems that exists in some limits and ties with essentially the motion of an electron in a random pi flux background, which leads to Anders localization. But in this case, it's Anders localization of emergent quasiparticles. And it also leads to very interesting thermodynamic response, which are really a signature of these mutual statistics. One has to do strong approximations in order to make any progress in this case, because it's a very difficult problem. You're tackling quantum mechanics at finite temperature and largely out of equilibrium. And some of the most difficult and most challenging issues in modern condensed matter physics, really. One has to do some kind of approximation about the timescales on which the spin-ons and the visons are moving. If you think about an energy being essentially an inverse time, you can say that the spin-on characteristic timescale is 1 over its hopping, t. The vison characteristic timescale, because they are thermal, is 1 over temperature, which is much larger than 1 over t, so they are essentially static. And you can hope that a Born-Oppenheimer type approximation is really what you want. You take the visons to be static and the spin-on zipping around and equilibrating or exhibiting all the dynamics properties within a time scale in which the visons are static. But of course, these are only approximations, and really understanding what happens beyond them is one of the big challenges that will be very difficult to tackle. But within these two working assumptions, one can make reasonable progress, and Olli has been able to make really some impressive progress in this case, leading to understanding the spin-on dynamics when the Weisern background is completely static, when this localization physics that I was mentioning earlier, and also instead to see a la Born-Oppenheimer, like density functional type of calculations, how the Weisern relax if the spin-ons remain instantaneously in equilibrium. And there are some very interesting correlations that might be able to highlight some experimentally relevant, as a matter of fact, smoking gun evidence of the presence of these anionic statistics and therefore of the quantum spin liquid behavior in these systems. Okay, with that, I think I'm coming close to the end. There were a few slides that I wanted to flash about all of these results that are very interesting, but I flashed the relative references and I will leave you to it. It would have been probably too much anyway for this general audience presentation. So let me bring back everyone to an overview of the talk. I hope that I managed to introduce the concept of frustration in magnetic systems. I illustrated, hopefully, how it makes a difference with respect to conventional magnetism and how it opens this window into an unusual and interesting regime that is usually referred as to spin liquids or spin liquid phase. I also hope that, at least at a classical statistical mechanical level, I managed to convey a bit of the understanding and an interest in these spin liquid phases through the properties of their excitations. And by introducing them, I also hinted at the fact that any effective modeling through this understanding of the excitation is actually very powerful to make progress in modeling, predicting behavior, or comparing to experiments for this type of systems that are otherwise very complex, strongly correlated many-body magnets. Amongst the property of the excitations, at the classical level, I hinted at this fractionalization and deconfinement that leads to reaction diffusion processes being important for these systems. And I only was able to hint at emergent symmetries. I did not cover the topic of entropic interactions. But I mentioned them as buzzwords if people want to follow them up. At the quantum level, we've seen that the situation gets even more complex. Typically, the excitations you have at the classical level will be endowed with other dual type of quasiparticles, and the statistics and their interplay can become really non-trivial, producing phenomena in quantum mechanics that we thought would have been impossible prior to our understanding of fractional quantum Hall and later spin liquids. And then I really rushed to give you just a flavor, probably too technical and too in-depth, but hopefully enough to simulate a bit of curiosity and intrigue and interest, and or at least give a sense into which this talk ultimately is background knowledge, but it goes all the way into touching some really modern topical condensed matter physics. And I gave a flavor about what behavior we may expect in quantum spin liquids and where we can encounter interesting physics due to this quasi-particle excitations, and focusing in particular on this intermediate temperature regime where we have several interesting points from having this classical and quantum behavior together, which is largely uncharted territory for our understanding to date, but also the first regime where you can possibly see signatures of quantum spin liquid behavior that will become then very important for experiment, looking for candidate materials for this type of systems. And with that, I come to a close. I thank you very much for your time and patience in my presentation. I hope it wasn't too far off the mark. And I thank, in closing again, my PhD student, Olli Hart, for all his hard work that he has done in understanding these very difficult systems. Thank you. This is also the point in time where you're most welcome. I was going to say, without any feedback, audio, video, or any such, I am talking to a computer screen and staring at the chat. Perfect.
Okay, I'm going to break up from him a little bit and share a few more things on quasiparticles.
In a world where particles aren't what they seem. Welcome to the realm of quasiparticles, the shapeshifters of physics. These emergent phenomena behave like particles, but arise from collective interactions in complex systems. They're nature's way of simplifying the seemingly unsolvable. Quasiparticles emerge from collective properties, allowing physicists to model intricate systems as if they were individual particles. With properties like mass, charge, and spin, they're the master illusionists of the quantum world. From phonons vibrating through solids to magnons dancing in magnetic fields, quasiparticles are everywhere. Excitons pair up in semiconductors, while polarons surf on waves of lattice distortions. And don't forget anyone's, the rebels of quantum statistics. These mathematical marvels help us grasp superconductivity, magnetism, and even quantum computing. Remember, in the quantum realm, sometimes the whole is simpler than the sum of its parts. Imagine.
Love it. All right, one more video just to further explain quasiparticles, because he's getting more into the magnetic properties and stuff like that. Okay, so this is chiral. I don't know if that's how you pronounce it. Magnetic effect in condensed matter. And this is from 7 years ago.
Were contemporaries in our graduate school days. We were friendly competitors in superconductivity. After he graduated from PhD in Iowa State, at the time a very strong superconductivity program there, he joined Brookhaven as a postdoc, and then stayed there. Now he's the head of the superconductivity.
It is electricity. I think everybody knows that. Okay. The reason I do that way, go this low, is that early days is that I try to help you, some of the students, to understand, appreciate this current magnetic effect in condensed matters. And I'll bring some of the common things we know for many years and to draw some comparison and to see how this current magnetic effect can be potentially be a driving force or disruptive force for the 21st century technology in electronics and optics. Now we know that we own today's world to a man did experiment in the summer of 1831. That's Michael Faraday. He's the one who actually, together with Lenz, discovered electromagnetic inductions. That is the basis for the electricity generators. If you have a closed circuit and you change the magnetic flux inside, and you generate electricity, right? That is the basic how you
Changing the magnetic
generate
flux.
electricity in a machine. Now, several years later, or maybe 10 years later, and it was found that the electricity produced the heating. It's called resistive heating. Now we also call it Joule heating there. And this is interesting, okay? Because this tells you that electricity passing a circuit has a resistance. Okay? And actually, much earlier, in 1827, and the relation between the electric resistance, electric current, and voltage has been formulated in Ohm's law there, and it's expressed here. Now, in terms of today's language, we say that a resistive heating is an irreversible process. Once you generate heat, you have increase of entropy, right? According to second law of thermodynamics over there, this process is not reversible, right? It generates error of time. So this is dissipative. Now, if you have a process which does not break, now we call it time reversal symmetry here because the reverse times is not the same for the resistive heating. Now, if you have a process is totally reversible, then you can reverse it in time. That means it does not break time reversal symmetry over there. There should be no dissipation because there's no entropy change. So in that sense, that if a process does not break time reversal symmetry there, it intrinsically could be a dissipationless. And that's something I want you to keep in mind for our students over there. Now, this has been known for years, but we actually don't know what's actually happening inside. What is the carrier for electricity? That's until 1897 when Thomson discovered electrons, it turns out that the electron is the carrier for electricity. Right? Now, the microscopic theories come up a few years later by Drew. He say that if you have electrons moving in the metals and they will hit something, like defects, and also lattice, okay, and you will produce resistance. Any non-zero temperatures, thermal energies will result in the vibration lattice, and that's the phonon, right? You quantize it as a phonon. So electron phonon is always there at a non-zero temperature, and it will always have resistance. That perception has been there for quite some time. But however, 10 years later, it was found that you can actually have something which totally have zero resistance, okay? And that's superconductivity. It was discovered by the Dutch physicist Kamil Onis. He found that if you have, during the experiment, you study the resistance of mercury, and you cool it at the temperatures close to liquid and nitrogen, liquid helium temperature, 4.2 Kelvin, you found that resistance totally disappears. It's not just small. It is actually zero. In today's world, we understand that. So this is called superconductivity. Superconductivity is the backbone for the MRI machines. And there's a superconducting magnet for the various accelerators there. Because the piece of superconductor wires can carry 100 times more current as compared to copper wires over there. So in last 10 years or so, I have been involved with the development of some of the high temperature superconductors and in the electricity generations, transmission, and storage over there. Now, this is actually not many material can do that. You can do all these things, storage, transmission, and generations. A superconductor can do that. And I have been involved with this development of cements, superconducting magnetic energy storage device. Basically, if you have a coils over there, because there's no resistance, if you lock in the current in the coils there, the current will be there steady forever, as this energy is a magnetic field energy over there. So it's like a battery, but this battery can last forever, right? But if you someday you want to use it, you open up the switch, you can drain the current out, and the draining of the current is very fast. So this is very good for the energy storage. You can make the coils as a magnet, and you can drive a machine, this rotary machine. For instance, I led a program on the wind turbine drive. We developed some of the coils for the 10 megawatt electric machines for the wind turbine generators. And also, of course, transmission. You transmit electricity without resistance, great. And that's always the high temperature superconductors. But if you look at this axis, this is not really high temperature superconductors. This is still at the liquid nitrogen temperature for use, 77 Kelvin. When we talk about high temperature, people will think about something on your furnace. That's really high temperature. We don't even have a room temperature superconductors these days, right? So so why we don't have a room temperature superconductors over there? Intrinsically, our superconductors is pretty weak. Okay, the microscopic understanding of the theories took many years. Okay, the first come in 1935. London brothers put the two equations. This is phenomenological equations to show the behavior, electromagnetic response in the superconductors. First equation described the ballistic acceleration of superconducting currents by transit electric field. The second one described the Meissner effect there. Okay. Now, the microscope described what happened to superconductivity is that it turns out the electron does not work in by itself, does not move in by itself. Individually, they have to form the pairs. And we know that the pairs is called Cooper pairs. That's your faculty, right? So that's the Cooper pairs. They say that because two electrons have the same charge, they will repel each other. You want to bring them together, you have to provide some of the glue, right? So this is glue, but the glue is very weak to bring two electrons together. So, and also, even though you have the Cooper pairs, this is the boson there, you're not naturally have a superconductivity. Today I have an opportunity to talk to Jim about his superconductor metal insulating, superconductor insulating transition over there. You have this boson. If you don't have the global macroscopic coherence in the ground state for the condensate states over there, you still have dissipations. So it's only that you have this condensate state over there, you can have a superconductor. It turns out that all the glue is weak, condensate state, very easy to break up by the thermal energy excitation over there. So that's why it's difficult to get room temperature superconductors. Okay. So then the question is that, is there any other ways to transfer charge without dissipation? And can you do that at a high temperature? possibly at room temperature. And if we can do that, of course, that's going to be disruptive technology to take on many challenges we face today. So this is something is really inspires to see. And then people try to do that. And we don't have much success until last 10 years or so. Even though some of the theories is there and prediction there, and experiment actually show up is that there are, at least I can show the two of them. It turns out the edge state in topology insulators is possible one way to transfer charge without resistance, because those states are protected by topology over there, and backward scattering is limited. Okay, sometimes it's totally blocked. Okay, however, this is the edge state is the same thing that if you have bulk material as the insulator edge on the surface is conducting, the cross section is not that large, right? If you want to transfer massive amount of current, it's difficult just from the edge or surface. You want to have a bulk, right? The bulk states actually happen in the chiral-magnetic effect. And this bulk states can be used as a way to transfer the charge without resistance and possibly the higher temperature. And that's the topic I'm going to talk about today. So I hope I give you some of the background to show that if we can understand this chiral-magnetic effect and then we can use it, it's probably revolutionary. Okay. So and all these things actually have something related to the Nobel Prize winner here today. And they are all the topological phase transition here. It is protected topology. So go back to the 2016 Nobel Prize over there. And all these effects today show that it has a lot to do with topological phase transition here. Okay. So what is the chiral-magnetic effect? And this concept is coming from the relativistic quantum field theory. It is the generation of electric current by the chirality imbalance between left-handed and right-handed fermions in the magnetic field. Fukushima and Kaze formulated some of the things for quark-gluon plasma, the CME or chiral-magnetic effect over there. So Kaze is a collaborator with me, and I'm really happy to have him around because I can learn a lot from him. So if there are some things I can understand in theory, I can have someone to ask for that. If something theory goes wrong, I couldn't answer the questions, I will ask the guys, ask Dima. Don't ask me because I'm an experimentalist. So that's very nice to have such a collaborator there. So now this equation shows you that it's a very simple equation, right? This is vectors and it's a scalar there, right? And it shows chiral-magnetic. This equation actually is very unique. Okay. Now, if you look at time reversible symmetry here, I just simply put it here. What you do here is that you do a time reversal, you change it from t to minus t, and if you look at the ohmic conductivity, and the equations change it to the minus here. There's a minus half here because j is t odd and b is t odd, e is t even there. You just do the time transformation, and that breaks the time reversal symmetry, right? It's right there, and it's dissipative. I already told you. If we look at the first London equations over there, it does not. Okay, this is invariant in the time transformation over there, and it's non-dissipative. And if we do the chiral-magnetic effect the same way there.
Okay, that was kind of boring, respectfully. There's another one here. Magnetic monopoles in spin ice by Dr. Felix Flicker. Anyway.
Perfect. It's online already, but I'm glad to hear it's a fresh audience. So this evening I would like to tell you about an expedition that took place to scour the ices in search of the North Pole. Now, you're probably all thinking, or I hope you're thinking, that I think we already did that about 100 years ago, finding the North Pole. Well, the purpose of this talk is not to tell you about finding the North Pole of the Earth, but about finding the North Pole of the magnet without the South, what's called a magnetic monopole. And the place we'll be searching is not the ices of the North Pole, but a certain material called spin ice. Has anyone heard of any of this stuff before? I hope not, but if you have, then, well, magnets maybe. Okay. The one thing I need you to be able to know, and I suspect you will do, is if I take a magnet and I try to, so this is the North Pole, say, this is the South, and I chop it in half and pull the two halves apart, one of two things could happen. Either I could end up with a North Pole in my left hand and a South in the right. Who thinks that happens? The other thing that could happen is that I end up with a North Pole and a South Pole in both hands. Who thinks that happens? All right, perfect. We're on the same page. All right, that's all you need to know for this talk. So I'm going to keep up this theme of early 20th century exploration of poles, just because I wanted to give the talk a bit of a theme on top of the physics. So I've made this map, I made it a while ago now. Here's the North Pole. And here we're going to start off down here in Cambridge. I'm going to tell you about the challenge that we're going to face. What are magnetic monopoles and why should we be interested in them? I'll give you a little bit of background on the subject. Then I'll tell you about the expedition, the route we took on this expedition. And that was the heading off, here we go, off on our journey. The idea is we're going to look for these magnetic monopoles in particular materials called spin ices. So I'll tell you about these spin ices, how they work, and why they should contain magnetic monopoles. Next, you'll get the expedition itself. So this was an experiment that was carried out a few years ago now, I think back in about 2020. And I was involved as a theorist. I don't do any experimental work, but some collaborators of mine did this very nice experiment that I'd like to tell you about. And that is searching for these magnetic monopoles using noise. And I'll explain what I mean by that and play some recordings. And finally, rather than returning home on our expedition, we're going to shoot off the edge of the map in search of new frontiers. So when I first put this talk together a few years ago, I would tell you about applications of this stuff, like a bit beyond theoretical physics. What can we do with these things at a kind of societal level? Now, the reason I wanted to talk about this subject again is because there is an update here. And I'd like to tell you about some of the more recent theoretical work that's taken place in this subject very recently, last year. Okay, so we'll start at the beginning with the challenge, magnetic monopoles. So what are they? Well, we can go back, sticking with our sort of explorer theme. Here we go with Michael Faraday, one of the pioneers of the study of electricity and magnetism. And as I think everyone here probably knows, Michael Faraday was the person who understood that electricity and magnetism are really kind of two sides of the same coin, right? And in particular, here are some of his drawings from his sketchbooks, by the way. His notebooks, he kept these kind of meticulous notebooks, which he bound himself, and he's got these very nice drawings. He's also got, this is a page of his book where he's stuck some resin over the page, and he's put a magnet beneath it, and he's sprinkled iron filings over the top, right? I did this when I was in primary school, so when we were about 5, and here Michael Faraday is doing it to demonstrate the existence of the two poles of the magnet. So there's some very fascinating stuff in his beautiful books. The bit that we're interested in is this page here, where he shows a picture just up there. Sorry, I don't have a pointer, but there's the top picture there, or the second from top, is a coil of wire. And he's drawn that a magnet passing through that coil of wire will induce a current in the wire. So that's being detected by the thing off on the left there. And so these days, as I think everyone here knows, a moving magnet can create an electric current. And similarly, if you reverse the story and you say, I want to send an electric current through that coil of wire, you'll generate a magnetic field. Okay, is this all sounding very familiar to everyone? No? Yes? Okay, good. Please say, if you want me to stop or explain anything in more detail, please ask. Good, so we have electricity and we have magnetism, and they seem to be two sides of the same coin. However, there's a major difference between the two, which is that you can have electric charge. For example, you can take a balloon and you can rub it on your tweed suit, and you bring your balloon near your hair, and your hair will get attracted to the balloon, right? Another familiar story. And that's because you're charging the balloon up, either with, I think, let's see, that state is great, positive. So actually, I think you rub the electrons off the balloon, and that causes it to be positively charged. Okay, and through that, you can attract your hair to the balloon. But the same isn't true of magnetism. There's no way to sort of induce a magnetic charge onto something. I can't cause a balloon to be magnetically charged and attract things using magnetism. So if you were to write down a list of the rules of electricity and magnetism, Faraday didn't do this, but one of his results ended up being in this list of rules. People here who are physics undergraduates will know these Maxwell's equations. And if you write them all out, they're beautifully symmetric between electricity and magnetism. Except for there's one that's different, where it says that electric charge exists, magnetic charge doesn't exist. We can have sources and sinks of electric fields, but you can't have sources and sinks of magnetic fields. So if you could, an electron is a source of an electric field, say. The electric field just comes out of an electron. but there is no equivalent elementary particle like an electron, which is just a source of magnetic field. Okay, so to answer, so at the start I asked you what happens if I take a magnet and I try and split it in half, and you all correctly identified that you end up with two smaller magnets. So why does this happen? Well, it's the same thing I was just saying. If let's zoom in to a smaller scale, we can define a magnetic field with this arrow pointing from north to south. And if we take a look inside the magnet, of course, we kind of conventionally color the ends blue and red, but of course, that's just us painting the magnet. If you look down on a smaller scale, you'll find that the magnet is made up of these magnetic domains, and each of those domains has its own magnetic field. They don't quite align, but they point roughly in the same direction. And the overall magnetic field that you get by adding them all up gives you the magnetic field of the whole thing. All sounding quite familiar? Good. And if you chop the magnet in half and separate the two halves, then each half is still made up of magnetic domains in exactly the same way. So of course, each still has a north pole and a south pole. Okay, well, you could say, what happens if I try and chop a domain in half? Well, if I look down on the atomic scale inside a domain, I'll find that each domain is made up of atoms, or possibly ions, electrically charged atoms. And each of those will have its own magnetic field. And each of those will be pointing in the same direction within a domain. So these circles are supposed to represent ions or atoms. And the little arrow is, again, the magnetic field. So if you chop a domain in half and separate it, well, it's made up of atoms or ions, each of which still has its own magnetic field with its north and its south pole. So it still has a north pole and a south. So then you could say, what happens if I chop an atom in half? But of course, you can't do that, so you get stuck there. So that's kind of simple explanation as to why you can't separate the north pole from the south pole. However much you chop it up, you've always got a north and a south. But if you think a bit more about this final answer you get to, there's still a mystery there. Because you could say, well, how is that thing, why does that thing have a north pole and a south pole? And the answer comes back to Faraday. It's that we have electrons with their electric charge. And if you were to take an electron and move it in a circle, then it would generate a magnetic field, right? Because this is what Faraday showed us. You make the electric current go in a loop, and you'll generate a magnetic field. I think of it, if I take an electron, I move it clockwise. So I think if I go like this, then it looks like a north pole to you, okay? And okay, the electrons in atoms, they're doing something quantum mechanical. They're not exactly just moving around in a circle, but they're doing a kind of quantum mechanical version of it. But nevertheless, the magnetic field is being generated by something like the flow of electric current. So you take the electric charge and you move it in a loop, and that gives you your magnetic field. But if I take my electron and I move it in a clockwise direction, it looks like a north pole. Well, if I just keep doing exactly the same thing and I turn around, then it should now look like it's going anti-clockwise, and therefore looks like a south pole. Okay, so if I'm generating magnetic fields by taking electric charge and moving them in a circle, then you must get the north pole and the south pole together, because it depends on if it's going clockwise or anti-clockwise, and clockwise motion viewed from the other side is anti-clockwise motion. They're really the same thing. So then you could say, well, okay, so philosophically, I can't even imagine then trying to separate the north pole of a magnet from the south. But the way to try and do it, if you could do it, would be to look for a new type of particle, like an electron, but one that's a source of magnetic field rather than electric field. And that's what would be called a magnetic monopole. Is that clear? Okay, good. So the quantum theory of this was come up with by Paul Dirac. So he's famously got his PhD here in Cambridge. I'm contractually obliged to point out that he did his undergraduate degree in Bristol, actually in engineering. So Paul Dirac worked out many important things in quantum mechanics. He was the first person to deduce the existence of antiparticles. So for an electron with its negative electric charge, there's a positron, which is in other ways identical, but has a positive electric charge. And another thing he proposed was, he said, well, let's imagine that a particle, a magnetic monopole, does exist. What can we deduce from that? Is there any way to sort of measure the existence of these things? So he developed the quantum theory of the magnetic monopole, and this was back in 1931. And if you're a physicist, you might like to take a look at that paper, because it is surprisingly readable, and it's completely modern in its outlook. There's nothing there that's wrong or anything like that. And he made some really fascinating predictions based on this. So you could say, well, we've looked for all the elementary particles and we found electrons, but we haven't found magnetic monopoles. That doesn't necessarily mean they don't exist. It could just be that they're very heavy, right? Heavier particles are harder to to create, or they require more energy to create. If they're heavy enough, you wouldn't be able to create them even in the Large Hadron Collider. You couldn't make them in any CERN or anything like that. And there's no like physical limit on saying how heavy or light a particle has to be a priori, right? So we've got limits as to what we can look for. It could just be that these things are too heavy to find. But there are other consequences of their existence, and Dirac worked out a really interesting one. And Dirac's deduction has led to a lot of people believing that these magnetic monopoles should exist, even though we've never seen one. And so what it was that he deduced, and I won't go into the details of how he deduced it, but if you're really into this and you're quite mathematical in your physics outlook, you might like to take a look at his work. He deduced that if you did have a magnetic monopole, it would cause both electric charge and magnetic charge to be quantized. They would both have to come in integer multiples of some basic amount. So, for example, if I took that balloon and I rub it on my tweed suit and put it in my hair and it attracts the hair, well, in principle, you could try and work out how much charge is on the balloon based on how strongly it wants to attract the hair, right? Okay, we can do this a bit more precisely. There's famously the Millikan experiment measures the charge on an electron quite precisely. Now, in principle, a priori, you might have imagined that the balloon could have any amount of charge on it. But if you measure it really precisely, you'll find that it's always integer multiples of some basic amount. But it turns out that there's no real fundamental mathematical reason why this is required in physics. The laws of physics would seem to work if you allowed charge to take a continuous range of values. So it could be like an electron charge, or it could be like 1.2 times an electron charge, something like that. But that's not the case. We find everything comes in integer multiples, very precisely defined. Okay, and it turns out that in the nearly 100 years since Dirac's work, we don't have a better explanation as to why electric charge is quantized. It's quite a big open mystery. So a lot of our leading theories of particle physics try to address this point, things like grand unified theories and string theory and these sorts of things, quantum gravity. All this stuff tries to explain this as one of the various mysteries that are still open. And it turns out that one way or another, they all end up evoking Dirac's argument about magnetic monopoles. So it might not be obvious that you have magnetic monopoles, but you do in your theory if you get this charge quantization for all the cases we've seen so far. Did you follow the logic? So it doesn't like logically prove their existence, the fact that we see that charge is quantized, because something else could be causing it. But in nearly 100 years, we don't actually have any other explanations as to what could cause this thing to happen. So that's quite a good argument that probably these things should exist. And quite interestingly, they could be very rare. In fact, you'd only need one magnetic monopole in the entire Hubble volume to cause all electric charge to be quantized. So that would explain why you haven't found one, because it's just sat out there in space somewhere. There might only be one in the whole universe. Okay, so that's what a magnetic monopole is, and that's why we might expect to see them, but we've looked for them. In fact, there's ongoing searches, including at CERN, for magnetic monopoles, and we've never found one. Okay, there was potentially exactly one measurement of one, but we now suspect probably that was an error. It was like 45 years ago. Okay, so I've presented the challenge. What are magnetic monopoles, and why do we like them as physicists? Why might we expect them to exist, but unfortunately we haven't found them. So let me tell you, here they are. There's a broken magnet, just the North Pole without the South, and vice versa. Sort of cartoon of it. Okay, but let me tell you about the route that we're going to take to actually try and find these magnetic monopoles. Now, I've told you that we can't find them. And the trick is to look in materials called spin ices. So all the stuff I was just telling you about was a story from elementary particle physics, right? I was talking about elementary particles like electrons. And we could define an elementary particle. My kind of simple definition of one is that it's something that can exist by itself in the vacuum of space and can't be reduced to other things with that property. It might not be a totally watertight definition, but it does the job, I think. So an electron would be an example. An electron can exist by itself, and an electron isn't made up of other things that could also exist by themselves. Okay? But an atom, for example, wouldn't be an elementary particle. It can exist by itself in space, but it's made up of other things that could do that, electrons, protons, and neutrons. Okay, let's go with that definition. Then elementary particle physics is the study of those elementary particles. Now, I'm a theoretical physicist, but I'm not a particle physicist. I'm a condensed matter physicist. Has anyone heard of that? Hopefully, undergraduates have at least. Generally, when I speak to people who aren't sort of working as physicists, they often haven't heard of the subject. But it's actually the biggest subject in physics. It's about a third of all physicists work in condensed matter. But actually, it tends not to have been heard of, whereas particle physics has. So The difference is that whereas particle physics will study elementary particles, condensed matter physics studies properties that emerge from the interactions of many different particles. But I would argue that it's fundamentally the same thing you're doing. So I'm assuming some of you, I've got probably a more technical audience than I would usually have, so I'll go into a bit more detail on this point. It's a point I've been hammering home for a while in a different talk. But it's kind of easy to think, well, the real things are things like electrons, right? And the universe is built up of things like that. And there are these other particles that come about when you have like a lump of matter. There are emergent properties that come about which aren't present at the level of individual elementary particles. So we call these things emergent quasiparticles. And it's tempting to think that they're not exactly real, they're kind of just emergent phenomena, right? A good example of one is that an elementary particle that you've probably heard of is the photon, right? It's a particle of light. So if you have a classical description of light, you can say it's like a wave. And then you can give a second quantized description of it using quantum field theory. And you can say, okay, well, actually, I can describe it as made up of individual particles, and those things are photons. And a photon can exist by itself in the vacuum of space, and it can't be reduced to other things with that property. So it's an elementary particle. Now, sound is also a wave, right, classically. And when sound travels through a material, in particular a crystal, you can also give it a quantum description. You can second quantize that description, and you can describe it as being conveyed by particles. And we call those particles phonons rather than photons. And in a sense, it's like, if I hit one edge of a crystal, a wave travels through it. It's vibrations passing through the material. So in a sense, it's just kind of the atoms vibrating about their original positions. But actually, in the mathematical sense that we describe it, using quantum field theory, it's exactly the same maths you use to describe something like the electron just sitting by itself in space, or a photon sitting by itself, shooting off by itself in space. The maths is the same. Okay. And you might say, well, the photon, the electron, those things are kind of real because they're not coming about through the behavior of other stuff. But in a sense, they kind of are, because the electron that we describe, if you go and look up its details in the particle data booklet, those things are not the things that appear originally in the quantum field theory. If you look at it, what you have is a heavy renormalization of those properties. Right? You have this kind of imaginary particle that never gets measured, and then it gets renormalized. You get like vacuum fluctuations, these kinds of things that change the properties into the thing that you end up measuring. And actually, mathematically, the whole process is identical. So I would say that the way I look at condensed matter physics is it's very similar to particle physics. It's just the objects of study are slightly different. But at a mathematical level, it's very similar. So we study these things like phonons, things that come about through the interactions of many other particles. And typically we're thinking we've got like a lump of stuff, like a crystal, and what things can exist in there. And just like a phonon can't exist in the vacuum of space, so it's not an elementary particle, it can't do that simply because sound can't travel through space, right? And I defined an elementary particle to be something that can exist by itself in space and can't be reduced to other things with that property. So sound can't go through space, so phonons can't be elementary particles, but they can exist inside materials. And so you see these emergent quasiparticles can exist when they couldn't possibly exist as elementary particles. So that's my personal excitement about this subject, is that we get to study a range of things that couldn't otherwise exist. And magnetic monopoles are one of the things that we're searching for, as well as particle physicists. So let me tell you how you could get a magnetic monopole in principle in a material, even though you can't get a magnetic monopole as an elementary particle, or at least we haven't seen them in that sense. And it's actually a fairly simple magic trick, and probably a trick you've seen before. Let me demonstrate it with my thumb first. If I wanted to take the end off my thumb and carry it around and then stick it back on, and without causing a load of mess, you might say, well, that's impossible. It's going to cause a lot of mess without any possibility of being mess-free. But in fact, as you've probably seen, you can take your thumb like this and you can pull it off, and look, my thumb has come off, and it wasn't a total mess, and now it's gone back on. All right, you've seen that trick before, I'm sure you have. And so I hope I'm not ruining the trick for you to explain how it was done. The way it worked was that you thought I had a single thumb, and I pulled the end off it, and there it goes, and it was mess-free. But in fact, I had a second thumb hidden on my left hand over here. And what I did was I take the two thumbs, and using two thumbs, I can make it look like I've got two half thumbs. Okay, well, it's a kind of naff magic trick. But we can do that same naff magic trick in real materials And then we call it fractionalization, which sounds a lot more technical. So let me tell you about how it works here. Imagine you've got a line of bar magnets and you stick them like this. And then, of course, they'll want to point north, south, north, south. Okay? And each of them has a north pole and a south pole. And then let's flip one of them. Let's take the whole bit and flip it around. And then imagine you kind of blur your eyes so that if there's a north next to a south, the blue and red kind of merge into nothing. But when there's a double north next to a double south, we see that concentrated region of north or south. Okay? So actually, in a technical sense again, this is a source and sink of magnetization or magnetic field. And if we flip a magnet, we can move the concentrated north away from the concentrated south, right? And so these things become emergent degrees of freedom that can move independently. But that's exactly what we're looking for when we're looking for an emergent quasiparticle. And you see that each of them individually, this one just has a north pole and that one just has a south pole. So you've done it by taking lots of things that have both a north and a south. You can get an emergent thing out of this that looks very much like a magnetic monopole. So that's the basic idea of the trick. Let me show you it in 2 dimensions. So imagine you place magnets on a grid like this. Then how do they want to point now? Before they just pointed north-south. Well, now they've got a few options because you just want to have 2 norths point in and 2 souths point in. That's the best you can do, right? Because north and south don't want to be next to each other. But if 4 of them are meeting, the best you can do is 2 in and 2 out. If we're thinking of norths. Okay. So they might do something like this. And again, if I take one and I flip it, then I get a concentrated region of north next to a concentrated region of south, in this case, 3 norths and 3 souths. And subsequent flips can move them apart. And importantly, if I create another pair over here, so another north-south pair, if I can get any north next to any south, I can flip the magnet between them and make them disappear. Okay? So at a physics level, we're thinking this is if everything's 2 in, 2 out, in terms of norths, if it's got 2 north in and 2 north south, then it's like the vacuum of space. There's nothing there. When I flip a magnet, I create this concentrated region of north and concentrated region of south. That's like creating a particle-antiparticle pair, or a monopole and an anti-monopole. And if I can create any other particle-antiparticle pair, any particle can annihilate with any antiparticle. And again, it's exactly the story you'd want if you're thinking
quasi-particle
of
and an
elementary particles off in
I don't agree with
space.
everything he's
You
saying.
can create an electron-positron pair out of the vacuum.
But I could be wrong.
You can do it again, and you can put the electron from the first with the positron from the second and annihilate them again. Right? This is the same thing we're doing here. Okay, so that's the idea. What would be really nice is if this story came about for real in a real material. That's always what we're trying to do in condensed matter physics. The story was nice, but can we get it in reality? So here is the thing we're looking in. This is a crystal called spin ice. It's dysprosium titanate, this one. There's another one called holmium titanate, and there's maybe a couple more now. As this was grown by Prabhakaran, who's the crystal grower in Oxford. And if we look down on the atomic scale in this crystal, we find that the atoms do something like this. In fact, these are magnetic ions. These are these electrically charged atoms. And there are other atoms in here that I'm not showing you. So these would be the dysprosium atoms, for example. And they sit on the corners of these tetrahedra, right? A tetrahedron's a polyhedron with 4 corners. The way the structure works here, you take this big cube and you stack that, and you stack the cube in the obvious way, and that builds up the whole crystal. This is looking at it on the atomic scale. And within one of those cubes, the magnetic ions are placed like that. So this is called the pyrochlore structure. It's kind of complicated, but it's not too bad. And here are the what are called the spins. These are the magnetic fields of those individual ions. We call those a spin. And just like before, in fact, they're constrained by their environment so that they have to point directly towards the center or directly away from the center of the tetrahedron on which they live. So just like before, the best they can do in terms of minimizing their energy is to have 2 point in and 2 point out of every tetrahedron, because you don't want north and north to meet, but 2 of them have to, and then 2 souths to make it a bit better. Okay. Now there's 6 ways to choose 2 in, 2 out on a tetrahedron. So you end up with lots of different ways of choosing all these different configurations. And what we believe happens is that, so this would be like the ground state of this material, and this is called the spin ice state. So it's actually a new type of magnetism that you may have heard of, like ferromagnets, and perhaps you've heard of paramagnets. Those are the things that aren't magnetic, but they become magnetic when you put them in a magnetic field. There's a few types of magnetism that you may have heard of. This spin ice is really a different type of magnetism with really different properties. So we'll see some of these mysterious properties shortly. This was the idea. This is the ground states. When you cool it down to really low temperatures, this is the way the magnets want to arrange themselves, or one of the ways. And actually, when I say really low temperatures, we're talking about something like below about 2 Kelvin, so 2 degrees centigrade above absolute zero. And when you put a bit of energy in there, so you heat it up a bit, they're not going to be in the lowest energy state, 2 in, 2 out. Some will spontaneously flip into 3 in, 1 out, and 3 out, 1 in. So we'll get something like this. We flip a spin, and then we get a concentrated region of north next to a concentrated region of south, a source and sink of magnetization. And subsequent, getting had to open my emails in order to get Zoom working, or not working as it turns out. So you'll get updates on the skip coming to my house. So as we flip subsequent spins, the monopole and the antimonopole can move around, and if we can get any monopole next to any antimonopole, we can flip the spin connecting them and send them back to the vacuum. Okay, so it all works exactly as you'd have hoped. So this was, I want to highlight another Cambridge connection here. So that this brilliant story, which has inspired a whole field of physics essentially, was developed originally by these authors back in 2008. And Professor Claudio Castelnovo is here in Cambridge. Perhaps some of you know him. So he's going to come up again later in the story, but this story really is his. So people knew about spin ices, but this story of magnetic monopoles and spin ices was come up with by these authors, and it's really inspirational. Why is it called spin ice, you might ask? Perhaps it's because it's really cold. It's not. It's far colder than ice. There's a slightly subtler reason. So this is the structure of ice, of water ice. Okay, it's H2O molecules. And as you can see, the oxygens are forming a regular structure. But next to each oxygen, there must be 2 hydrogens, because it's water molecules, H2O. And the way they arrange themselves, the hydrogens, there's like 4 bonds coming off the oxygen, and it's got to choose how to orient its 2 hydrogens. And in a sense, you could say it's like two hydrogens in and 2 hydrogens out, right? Along any given oxygen, the 4 bonds, 2 will have hydrogens on and 2 will have hydrogens like far away. And so you have this ability to choose multiple options within the ground state again. For physicists who've thought about this a little bit, who studied thermodynamics here? Did you enjoy it? I really liked it, but I had a great teacher, Steve Blundell, who worked with me on this stuff I'm going to tell you about. I know some people say it's outdated, but it's definitely not, in case anyone was thinking that. Now, one of the things you might have learned in thermodynamics was the third law. Does anyone remember the third law of thermodynamics? I'm putting you on the spot now. I see nods. Is anyone willing to sort of shout it out? No? All right, that's for putting you on the spot. It depends how you're taught it. But I was taught it by Steve Blundell, who was very careful with it and knew very much about ice and spin ice. And he said something like the entropy of an infinite perfect crystal should tend to 0 as the temperature tends to absolute 0, something like that. But there's a lot hidden in that infinite perfect crystal bit. Because both ice and spin ice, if you know, when you cool them down to the ground state, this would be at absolute 0 in principle, there's still disorder allowed there, right? Because I can choose how to place the ins and the outs in the magnets, or the ins and the outs in terms of these hydrogens. But if I can choose how I arrange things at absolute 0, then I seem to have some entropy left. I have some disorder available. It's not completely ordered. So this seems to violate a kind of naive statement of the third law of thermodynamics. And we had to be a bit more careful in our phrasing subsequent to this. So other people phrase it as now say the entropy has to tend to a constant as temperature tends to absolute 0. The infinite perfect crystal bit kind of covers your bases, because you would say this is not really a perfect crystal in a sense. Something a bit more serious going on, even with water ice. So it's this weird property that as you tend to absolute 0 in these materials, that's the ice bit from spin ice. Okay, so that's the story of these magnetic monopoles. We search these spin ices and we find them, but so far it's just been I've just told you that should be what's going on in that, but you need more than that. It's a nice story, but what's the evidence for that being the case? Okay, and there was plenty of evidence, but it's not exactly circumstantial, but we were missing what you might call the smoking gun evidence. That's the phrase everyone seems to use in this field. So what's the smoking gun evidence that this is the only possible explanation as to what's happening in spin ices at low temperatures? And depending on who you ask, we may or may not have had that before, and maybe we do now, but I'll tell you about a bit that I find quite convincing, but that perhaps it's still not the smoking gun. Tell me what you think afterwards. So I'm going to tell you about this expedition that was undertaken by a sort of international team that I had the good fortune to be involved in. So the principal people involved in this were Ritika Desad, who is an experimental physicist, and she was doing her PhD at the time. She was the lead experimentalist on this, and Frank Kirschner was kind of the lead numericist. So she was doing numerical simulations of what should happen on the atomic scale in these spin ice materials. So the way it worked was that Fran made some predictions. She gave a talk about them at a conference, and then very shortly after, remarkably shortly after, in fact, about a week later, we had an email from Seamus Davis, who was the sort of senior experimentalist on the project, saying that his student Ritika had they'd seen the talk at the conference, and they'd gone off and they'd done the measurements, and they confirmed the effect all within a week, which is not the time scale these things usually work on. Typically, you might sort of propose something, and maybe a few years later, someone's got round to trying to get funding to build the machine, and then a few more years later, maybe something happens. So you don't expect it to happen in a week. So let me tell you about what it is that Fran predicted and Ritika measured. A schematic of the setup. Let me just tell you about the prediction first. So originally, the idea when we were working on it, Fran's supervisor was Steve Blundell, who I mentioned before in Oxford. The idea was originally to use a very sensitive detector of magnetic fields, what's called an NV magnetometer, which you can place just next to the crystal, really close, like 50 nanometers away or something like that. And it can detect magnetic fields on the scale of a few atoms. It's really, really sensitive. So the idea was, if you cool these things down so there's hardly any of these magnetic monopoles, in principle, one might sort of hop along. Like I was showing, you can make them move by flipping those magnets. It could just sort of walk into the detector's range and out again, and you'd see a very distinctive signature of the magnetic field. Again, at a slightly more technical level, something that really made me believe in these things as like real things rather than just sort of a nice description, is that you can put the magnetic field detector outside the sample and measure the field coming off it, and you'll find that it's dropping off as 1/r² rather than 1/r³, which is what you'd find for dipoles. Right? So somehow you've got a load of magnetic dipoles with 1/r³, and they've added up their fields in such a way that the thing acts as if it's a moving monopole with 1/r². And you should be able to detect that in principle. But what Fran found is that with realistic experimental constraints, the temperatures at which you can operate don't allow you to get like single monopoles walking near your detector. You instead have loads and loads of monopoles. Okay, so it's a little bit like you've predicted the existence of a raindrop by saying, okay, if I go and listen for rain, I'll hear this sound, and it'll sound sort of like, I don't know, like flip, something like that. Okay, and then you go out to do the experiment. You say, okay, I was told if I go and stand under this cloud, I'm going to hear this plip sound. But of course, you don't hear a plip. You hear a kind of bit of raindrops at the same time. You don't get one. And it was very much like that here. The original prediction was to try and work out what it would sound like for a single monopole sound. What your magnetic field detector would detect for a single monopole, but you actually have loads and loads of them. So you get what's called noise, and typically noise is, this picture is somewhat irrelevant, sorry, I'm going to get rid of it for a second, let's get rid of everyone. So you might think of noise as the thing that ruins your measurements, right? You have the signal, then you have noise that messes it up. But actually, it turns out that there can be a lot of information in noise. There are different types of noise. So, can anyone name a type of noise? Okay, so white noise is maybe one that people have heard of. Has anyone heard of white noise? Okay, good, some have. Red noise, has anyone heard of that? A bit less known. Red noise would be if you remember the famous experiment of looking at a pollen grain in water, and it sort of jiggles around with Brownian motion, right? At each instant, its velocity is random, and there's a kind of white noise signal for its velocity. But the position as a function of time, it's random. It's being jolted randomly at each instant, but it's not jumping around randomly. It's sort of moving in a kind of jumping a small distance, but randomly each instant. So overall, it ends up moving with what's called red noise. So Brownian motion is described by red noise. So I had we're going to we're going to try and I'm going to get rid of information about skips while we're here. Okay, so I have a nice program for describing different colors of noise, as they're called. It was written by Leon Zaporsky, who was here in Cambridge doing his PhD until very recently. He's now moved off to MIT. But he wrote this while he was an undergraduate student that I was working with over in Oxford. So it's online. You feel free to play around with it. It's on his GitHub. So it lets you play different types of noise. Now, they don't sound great. I'm just going to warn you. Oh dear. I'm also going to hear myself talking if I unmute myself. That's not great. Perhaps I can. Sorry, give me a sec. Let me get rid of my microphone. That'll help. Oh, good. Okay. All right. So I still hear myself. All right. I'm going to stop talking and I'm going to play you some noise. It's not going to sound great. It'll be white noise. It's one of the worst things you can hear, but there's something instructive in listening to it. So here we go. I'll shut up. It's incredibly quiet. Unlike my own voice. You know what? I'm going to borrow this microphone. Perfect. Hello? Can you hear this? Oh. You're not hearing that at all, are you? Are you? This is a nightmare. The problem is that microphones then have noise suppression in them, so you try and play it and they just cuts it off. Yeah, let's just forget that. All right, we'll try it again. So that was white noise. It sounds awful. It goes. Let's try a bit of red noise now. So I'm going to pull it. You can pull this slider out. This is the interesting bit. So let's pull it right over to here. This would be red noise. Is the signal if you're interested. This is some more technical detail here that I'm going to go into. Let me play you a bit of red noise. Did you hear it? Not really. Okay, you know what? I'm just going to do it with my mouth. White noise sounds like shh. Red noise sounds like shh. Okay. So the idea is that you've got I think on this, I think we can see the picture of it down here. There we go. There's a bit of technical detail for you. So white noise has equal amounts of power at all octaves. Okay, so it's random, but it's sort of truly random in the sense that at all octaves, like if you go to a higher pitch, it's the same amount of noise. Red noise, the noise power decreases as you go up to higher frequencies. So higher frequencies are missing. It's named in analogy to light. So if you took a mix of all frequencies of light, you get white. But you could also take a random mix of frequencies and you cut out some of the shorter wavelengths. So keep some of the longer wavelengths and it would become red, or it would become pinker, right? So you can see it drops off like this. So so red noise has the noise spectral density, as it's called, decreasing as 1 over f squared. Okay, so it's an inverse square law. Pink noise is between white and red, and this is again the analogy. You take a mix, a random mix, but you can get it between the two. So let me put it around 1. So anything between 1 and 2 is typically called pink noise, and it's somewhere between the two. So if white noise sounds like shh, red noise, then pink is sort of like shh, okay, in between. You can imagine I'm playing with this high technology here. Okay, so Fran's prediction, and it's quite a remarkable one, was that if you take a crystal of spin ice and you put a magnetic field detector next to it, you'll measure noise. But if you look at the distribution of frequencies of that noise, even though there's randomness to it, the distribution will be skewed in such a way that you get more of the longer wavelengths than white noise, and you get less of them than red noise. Now, this is remarkable because if you take a paramagnet, this is the thing that's not magnetic, but you put it in a magnetic field, it becomes magnetic. Okay, if you take one of those, there's a very old theory that it's well known and well tested that every paramagnet will have perfect red noise in its magnetic field. Okay, it's a fairly simple calculation. So Fran was predicting that you get pink instead of red, and this was the signal that Ratika went off to measure. So let me get back to the equipment up here. There they are. Here's the device. So the trick as how they did it so quickly was that rather than try and place a magnetic field detector with these MV magnetometers, Ritika just took the spin ice crystal and she wrapped it in a coil of wire and connected that to a very sensitive detector of magnetic flux. It's called a superconducting quantum interference device, or SQUID. So hopefully this setup looks kind of familiar from the start of the talk. This is Faraday's picture from his notebook, where he showed that you take a coil of wire and you pass a magnet through it, you'll get a current in the wire. And in fact, that's exactly the same effect that Ritika ended up using. You really take a coil of wire and you connect it, in this case, to a flux detector. So this is the SQUID. I wanted to put a picture of a squid up there. It's actually, I think, like an octopus, but I wanted to keep with the Explorer theme. I was quite pleased with that. I made wrap its legs around the squid, which I was quite, that took some work. Okay, so this is the setup she built, and here's the result. So I have quite ingeniously, when I want to explain that the this noise thing, in some sense, it's an analogy, right? It's really you're detecting the magnetic field as a function of time, and you can Fourier transform that in the technical language, but you can work out what mix of frequencies are present in that signal, and then that is the thing that can be compared to noise in the sense of me going sh or sh, okay, right? So it's really a magnetic field, but you can actually do that. So your ear is sensitive to a range of frequencies, right? Like up to like from 20 hertz to 20 kilohertz or something. This squid is actually sensitive to an overlapping range of frequencies. The squid is sensitive up to about 2.5 kilohertz, I think. So it can't hear as much, as wide a range of frequencies as us. It's not hearing sound, it's detecting magnetic fields, but there's a highest frequency which it can detect. But it's within our auditory range. So you can convert the signal the squid is detecting into an actual sound, and you can just listen to what it's detecting sort of live. And so Ritika took a recording of this just to demonstrate what it is that they were hearing. And I've got the recording. We'll see if it works. It's going to be very quiet, of course. It is worth hearing if I can do it. Yeah, let's give this one more go with this microphone. Some people heard it, I think. Okay, so here's what Ritika heard. And so the first 3 seconds of this recording, it's going to be white noise before the sample goes in. And then the second 3 seconds is when the sample's gone in, and you should hear it turn into pink noise. So let's try this. Unmute. Did you hear it? It changed. Oh, off we go. Very good. I think that was very cool. I thought it was an excellent, there's no particular scientific content to it, but it was a very nice thing to hear that it's really working. So that was the prediction and then confirmation by Ritika. Good. All right. So that the colors of noise. Here's Leon Zaporsky, who made that colors of noise program. He's not here anymore, but hopefully some of you met him while he was. Okay. So I've told you about the expedition that took place to try and find these magnetic monopoles, and the trick turned out to be to recruit the help of this giant squid. And the trick was to listen for them rather than use any other of your sensory apparatus to look for them. Okay, so let me shoot off the edge of the screen in search of new frontiers. And I'm going to start by giving you an update on this story. How long do I have? I'm running a little bit short. Am I? Okay, we're doing that. So, okay, here's the new thing. And this is the reason I really wanted to talk about this, despite the fact that the work was done a few years ago now. The question remained, why do magnetic monopoles in spin ices make pink noise? Well, like, why are they doing that, whereas a normal paramagnet is making red noise? Red noise we can understand, right? It's the thing I said before with the Brownian motion. The pollen moves, the velocity changes randomly at each instant. So that's white noise. That seems kind of intuitive. You can then integrate white noise with respect to time, and you'll get red noise. And so the power, the noise spectral density goes as frequency to some power. It's gone from 0 to -2 in that process. So why would you get something that's between 1 and 2, and as it turns out, changing with temperature? And it's really hard to get this. There are many phenomena that show red noise. Paramagnets being one, pollen grains being another. There's plenty of others. Basically because a random walk gives you red noise. Okay, you take a thing and you let it jump a small amount in some random direction, and then you do it again and again. And the end process of that is something that we understand statistically very well. But trying to generate pink noise from some sort of microscopic model like that, like saying something's hopping around in a certain way, turns out to be impossibly hard. No one has a good model of how to do that, despite a great deal of work in this. So since about the 1970s, people have been claiming that pink noise is kind of ubiquitous in the real world. So I did my work experience as like a secondary school student at a speaker manufacturer. And when they build speaker cabinets, they want to check they don't resonate at certain frequencies, right? Because that would ruin the music. And so you want to play like an equal mix of all frequencies to check them all. So you could play white noise, but of course no one wants to listen to white noise because it's awful. So what they play in speaker cabinets to test them is pink noise. And they were explaining that they do this because that's believed to be a pretty much like average mix of the sorts of things people like to listen to. And it turns out there seems to be some basis for this. It's kind of pleasing to us, but it seems that's because it appears all over nature. So there are all sorts of claims to varying degrees of believability. So the tide times of the Nile are supposed to follow pink noise. If you look at the scene lengths in films, people have done statistical analyses of these and found that they follow a pink noise power law as well. Some of this is dodgy statistics, and we fell foul of some of that in our original analysis. It turns out actually that sampling can give you pink noise when you don't really have it, but there is now believed to be a real pink noise effect going on here. So why does it happen? And there's not many things you can think up that can do it, basically because if you take a random walk in any number of dimensions, you'll still get pink noise, okay? And that's the basis of basically everything we seem to understand in these statistical things, if you can map it to pink noise. Sorry, red noise. So one place where you can get pink noise, and we do understand it, is in a fractal. So I said if you hop in any number of dimensions, you'll get red noise. But actually that's only true if your number of dimensions is an integer. If you hop around in a number of dimensions that's not an integer, you can get pink noise, and that was already well understood. So here's a classic fractal. It's not entirely relevant, but it's the one that we're probably most familiar with. So we can take a triangle and delete a bit, delete another triangle out like this, and another one, and so on. Have I got one more? Yeah, I have. Okay, there's a Sierpinski triangle. And I do this an infinite number of times, and I end up with some stuff still there. If I imagine trying to hop around on this, when it was a triangle, if I could move anywhere in the white bit, I'm moving around in 2 dimensions, right? I can move across and up. But now how many dimensions am I moving in? I'm not really moving in 2 anymore because, in fact, you can make it so that all the area is gone. So it's not moving in 2 dimensions. But you're not moving in 1 dimension either, which would be moving back and forth along a line, because I can actually choose some directions. I can move around. So you can see in a sense that if something were hopping on this, it would be hopping in some number of dimensions between 1 and 2. You can work out what it is. It's a fractal dimension. Okay, so, oh, I had one more. There you go. So what's this got to do with magnetic monopoles and spin ice? So this is this new theory that's come out as to why they show pink noise. And actually, again, it was Professor Castelnovo here in Cambridge who worked this out, along with various other people. And the story is this. Let's take the simple picture of this 2-dimensional spin ice, where they're 2 in, 2 out everywhere, like the vacuum of space, and then we've got a pair of these monopoles. And I said, I can flip any magnet and I move them apart like this, right? And I said, if I can get any red next to any blue, I can flip the magnet between them and get them to annihilate back into the vacuum. But that was a bit of a lie, because say I'm here, say I want to move up instead of across. Well, if I flip that magnet, if we take a look at this, if I flip the magnet that's above it, I don't get 2 in, 2 out on that side and 3 in, 1 out above. I get 4 in, 0 out on that side. So that's like 2 monopoles now. And above, I get a new one that's blue. So if I flip that one, I create a new monopole-anti-monopole pair, and I've got the 2 monopoles on the same side. And bear in mind that they're magnetically charged. They want to repel each other, just like 2 electrons want to repel each other. So this would cost a huge amount of energy and doesn't want to happen. So in a sense, that direction is just disallowed to that monopole, okay? And if you take a look through all the possible places you can try and get to from that site, you'll find that all these different magnets can't be flipped. If you flip them, they create another monopole-anti-monopole pair and actually costs you loads of energy. So if we delete all the ones that can't be flipped, you end up creating a fractal again, or something that's very similar to one, okay? So it's not quite 2-dimensional anymore. It's not 1-dimensional either, much like hopping around on that Sierpinski triangle. So the fractal you're very close to is what's called a percolation cluster. It's another quite well-known fractal. Has anyone heard of percolation clusters? Okay, well, it's the thing you get when you do this, exact thing. You take things and you start deleting them out of some structure, and the idea of percolation, well, let me tell you the history of it, actually. So although fractals are typically thought of as being discovered around the 70s, maybe 80s, with the advent of computer programming, where I can do those pictures quite easily. The percolation cluster was actually understood earlier. To discover
All right, enough of him. I'm going to try one more video because I'm going to be obsessing over this for a while. And
atoms and sporks. And in this video, I want to talk.
This is what are quasiparticles, the real fake particles of the universe. It's from Atoms and Sporks.
About the incredible, varied, and fascinating menagerie of quantum particles that no one ever really talks about. Quasiparticles. So what are these quasiparticles? Well, if you have an interest in physics, which you know if you're watching this channel, that might be a pretty good bet, then chances are you've probably heard of these guys. These so-called fundamental particles of the standard model of physics. The 25 basic building blocks of all reality. Or are they? The thing is, for example, a particle of light, the photon, makes this list. But do you know what doesn't? A particle of sound. A particle of magnetism, a particle of charge fluctuation, hell, even a particle of superconductivity. And yet, these things do exist every bit as much as a photon, even if they don't always get the same attention. So in this video, we're going to learn a bit more about what these quasiparticles are and what they can do. Okay, let's start things off with a bit of a quick jaunt into physics history to the time of the Industrial Revolution. Now, during that time, a new physical theory was being slapped together in order to describe the behavior of these new fangled contraptions called heat engines. That theory was called thermodynamics, and it was a really big success. However, thermodynamics was also very much a macroscopic theory and cast things in terms of macroscopic quantities like gas pressure and temperature and heat flow, and it didn't really make any attempt to understand what a gas or temperature or heat really were at a fundamental microscopic level. That is, until what is called the kinetic theory of gases came along. The goal of this kinetic theory was pretty simple. There had already been this idea kicking around from things like the chemistry of reactions that matter at its most fundamental level was made of these little basic objects, which are atoms, and what kinetic theory did was try and describe this now well understood macroscopic thermodynamics behavior of gases in terms of a microscopic picture of trillions of these little atoms. Now, the way this was done is going to be very important to us as we talk about quasiparticles. So it's maybe worthwhile to go a bit deeper into the nuts and bolts of how this theory really worked. Basically, this kinetic theory posited three things. The first is that the macroscopic behavior of a gas was really the result of the microscopic behavior of bajillions and bajillions of basic natural objects. And I'm intentionally being a little vague and abstract here when I say basic natural object, though of course in the case of kinetic theory, those objects were either atoms or molecules. The second thing it assumed is that all those objects followed the same basic rule for their movement. Again, vague, I know, but in fancy talk, we say that each atom has a certain energy-momentum relationship, or dispersion relationship, that basically says how much momentum this object will have when given a certain amount of energy. Now, in the specific case of the kinetic theory of the late 19th century, physicists just assumed atoms were like little hard spheres, and so they assumed that their energy-momentum relationship was basically that of like a billiard ball, a so-called quadratic energy-momentum relationship. And finally, the third thing they assumed was that these basic objects were randomly scattering off one another. Basically trading energy and momentum until they reached a final unchanging sort of equilibrium average state. So those were the three things they posited: a basic object, an energy-momentum relation that each object followed, and the assumption that these objects were reaching an equilibrium state through scattering. And using that, they made this kinetic theory of gases, and it worked. They could start from this microscopic place with its three basic ingredients, and from that derive those macroscopic equations of thermodynamics. In essence, they provided some of the first convincing and quantitative scientific proof that a gas really was just a bunch of atoms zooming about and hitting each other. And I want to point something out right away. The basic object of this theory of gases was atoms, but atoms aren't fundamental particles. Of course, they didn't know that back then, but nowadays we know that atoms are made of electrons, protons, and neutrons. And although electrons are currently considered fundamental, protons and neutrons themselves, we now understand, are made of quarks. But, and this is the really important point, the natural object of a gas is not quarks. It is not free electrons, it is atoms. You could stare at the quantum theory of quarks all you wanted, and you would never understand how, say, the pressure of a gas changes as it's cycled through a heat engine. This is much the same as to why you can't understand, like, the macroeconomics of intra-European trade by studying the biology of human red blood cells, even though technically economies are, made of humans. Thermodynamics is what we call emergent physics of many atoms. It's macroscopic behavior that is more than just the sum of its parts individually. Or as the late physicist Philip W. Anderson put it, more is different. Furthermore, this trick 19th century physicists use of understanding macroscopic behavior through the lens of these three ingredients is something that can be applied in a lot more places than just gases. For example, a few decades later, physicists were really stumped in trying to understand what is called the thermal emission of light that happens from something like a hot wire. When you heat up something like a stovetop, it starts to glow red, and the spectrum or distribution of colors of that red glow was really impossible to understand for physics at the time. That is, and I fully admit I'm not being truly historical here, but until the physicist Max Planck basically said, screw it, in frustration, and even though he couldn't think of any physical reason why it should be true, he posited that this emitted light itself consisted of a basic unit, and that it followed a certain energy momentum relation or dispersion relation, and that they had reached a kind of equilibrium. And then he basically turned the mathematical crank, and it worked. And from that kind of desperate assumption, he had unwittingly proven the existence of the first true OG fundamental quantum particle, the photon. He basically assumed that such a wire was a gas, but not a gas of atoms, a gas of units of light, or photons.
Bingo.
And from that, he was
Void of
able to
electrons.
perfectly derive the way this thermal emission was found to really behave in experiment. So the first application of this approach gave us knowledge of atoms. The next, photons. What could possibly be next? Well, when Planck originally made his photon hypothesis, much of the physics community, in many ways including himself, were not exactly convinced these light particle things were real. But someone who did take them seriously was a little poorly known, almost forgotten physicist named Albert Einstein. And he too would have a crack at applying this approach. See, Einstein had basically actually done his PhD in the application of the kinetic theory of gases. So he knew that this approach works very well to replicate and explain the thermodynamics of gases. So he took the natural next step and turned to applying it to describe the thermodynamics of solids. Like with the kinetic theory of gases, Einstein imagined a solid as being made of bajillions and bajillions of atoms. But, unlike a gas, these atoms were in a rigid array or lattice and could not move freely. Rather, all they could really do was kind of oscillate or jiggle about on the spot. So their rule of motion wasn't the same, like zooming around like a billiard ball, but rather it was a rule of like a stationary oscillation about a fixed point. And Einstein's idea was to try this exact same quantization hypothesis out as worked so well before. In essence, like with photons, he assumed that these atomic oscillators couldn't take any energy they like, and instead could only accept certain clumps of oscillations. Again, just like before. And this is important to understand. The basic unit here isn't the atoms, but rather the oscillation of the atoms, which he assumed only came in units. So, like Planck assumed light came in units, and thus a hot wire was a gas of light quanta, Einstein assumed heat in a solid was a gas of atomic oscillation quanta. And doing this, he developed a model of the thermodynamics of solids that, well, almost worked. The problem he had was simple. He had guessed the wrong basic natural object. A solid is not just a bunch of independent vibrating atoms, like he assumed. The atoms are all chemically bonded with one another, like a network of springs. And if one moves, it pulls all the rest with it. Soon after Einstein released his only partially successful model, another physicist named Peter Debye made a small but important tweak with this in mind. Debye envisioned that the basic natural object was not an independent oscillation of individual atoms, but rather a collective oscillation of the entire lattice, basically a lattice wave. And, like Einstein and Planck, he did assume that this collective oscillation was quantized and could only come in discrete units. Now, these lattice oscillations are actually what sound is. Like, literally, sound is a wave in atomic displacements
So we're
moving
inside
through
a lattice
material.
wave.
That's what it is.
A contained
And
environment.
furthermore, if one looks at our second ingredient in our kinetic
Toroidal
theory
fields.
approach, our energy-momentum relationship, a spring lattice wave will actually have one that is very, very similar to an electromagnetic wave, a so-called linear relation. Because these lattice waves are sound, and because they are quantized, just like photons, and have a very similar energy-momentum relationship, we call them phonons. And Debye showed that just like the thermodynamics of gases could be explained as a gas of atoms, and how the light emission of hot objects could be explained as a gas of photons, the thermodynamics of solids could be explained as a gas of phonons. And where a photon is a quanta of an electromagnetic field and is considered a fundamental particle, a phonon, which is like a quanta of like a lattice field, if you like, or a network, is called a quasiparticle. If it's a quanta of light, it gets called fundamental. If it's a quanta of sound, it gets called quasi. And this approach
Why?
can be applied everywhere. For example, in a ferromagnet, like your fridge magnet, at absolute zero, all the so-called quantum spins, which are kind of like individual magnetic dipoles or like bar magnets, are all aligned in the same direction. That's what makes it a ferromagnet and gives it a permanent magnetic field. But if I then turn up the temperature from absolute zero, give it a little heat, then these spins can sort of jostle and tilt away from that special direction. And how do you think you describe the behavior of this system? By modeling a bunch of independent spins? No, you imagine a wave of magnetic deviation and then you quantize it. We call this quanta of magnetism a magnon. We're not very creative. And the thermodynamics of a ferromagnet is described by a magnon gas. And really, sure, there are only 25 particles in the standard model, but there are many, many more quasi-particles than that. There are quanta of the mobile charge in a metal, a plasmon. Quanta of the polarization of a material, polaritons. In what are called superfluids, a state of matter that happens when certain isotopes of helium are cooled to very, very low temperatures, you find two quasi-particles, phonons, and what are called rotons. In superconductors, much like with magnets, you have a quasi-particle of deviation from the superconducting ground states, and it has the absolute best name of all. They are called Bogleubans, named after Soviet physicist Nikolai Bogleubov. There are even quasi-particles made from combinations of quasi-particles of quasi-particles. For example, photons and phonons, when coupled, become phonon polaritons. Or quasi-electrons and so-called holes in semiconductors form quasi-particle states we called excitons. The variety of quasi-particles is vast and practically innumerable. But more than that, quasi-particles are fully described with the same language of quantum mechanics that fundamental particles are. And like those particles, they have certain quantum properties, the most famous being spin. A phonon comes in two varieties, spin 0 or spin 1. Magnons are spin 1, and so on. However, unlike fundamental particles, with quasi-particles, we can engineer and manipulate their properties by controlling material parameters like bonding strength or pressure. And because of this, we can design quasi-particles that have properties that are allowed by the laws of quantum physics, but that no known fundamental particle actually exhibits. For example, for fundamental particles, the value of this thing called quantum spin can only be either a fraction of 2 or a whole number. We call those where it's a fraction fermions and those where it's a whole number bosons. Well, you can actually make a quasi-particle that isn't a fermion or a boson, but, and again, we are not very creative, anyon, as in it can take any continuous spin value you like. Quantum mechanics allows it, and even though it might not exist in the larger universe, in the sort of tiny universe of certain special materials, it does exist. So at this point, hopefully I've convinced you that quasi-particles are kind of a very interesting extended menagerie of quantum particles that are capable of many, many incredible things beyond these very limited 25. However, I do know that sometimes when one first learns about quasi-particles, to some it seems like a bit of a trick. It seems like making a big deal about something mundane. A photon, now that's a particle. Atoms jostling in like a hunk of metal, that's not a particle, even if the math looks the same. Well, before we finish things off, to that hypothetical straw man, let me make one last claim. These guys here, these are quasi-particles too. You see, at extraordinarily high energies, like those only a fraction of a second after the Big Bang, these guys didn't exist. Rather, you had different particles that they were mostly like these guys, but with one big difference. None of them had any mass. All particles were massless in this epoch of our universe. So then what are these guys? These alleged fundamental particles? Well, these are basically what happens when you take those original massless particles and bundle in their interaction with what's called the Higgs field. The electron of the standard model, with its mass of 9.11 times 10 to the negative 31 kilograms, is an emergent dressed one that bundles together the original object and its interaction with the Higgs field. These are all dressed particles, even the massless photon. In this super high energy so-called electroweak epoch, there weren't photons and Z bosons, there were only massless B and W bosons. And finally, if you are still not convinced, if you still want to put these guys up on a pedestal, I would make the final argument that assuming something is fundamental, the end of the road, has historically been a very unsuccessful worldview. We used to think atoms were at the bottom. Then we learned they weren't. We learned that they were made of neutrons and protons. And now we know that those are also not fundamental. They are made of quarks. And we do currently think that quarks are fundamental. But are they? Not if, say, string theory is correct. They too could fall. But quasi-particles are forever. As we discussed, the basic object of a gas is an atom, not a quark, an atom. Nothing we learn about quarks will ever change that. All right, that's it, I think. If you like this video, please like and subscribe.
All right. I will possibly come on later and share my interview with Pat King. It's up on Spotify now if people want to take a look. And I was going to do current events as well, so I might do that at some point as well. But if not, and you don't come back on that note, I will leave it at that and hope that everyone has a wonderful rest of your day.